without further ado, I can start jumping through. Morris and I will trade things back and forth a little bit. Um, so, what are we going to talk about today? Just a very brief overview of, the ways RNG and hydrogen are used in the AGA study. Then we'll focus more on some of the RNG supply potential details that went into the study's work, and then also some of the use cases for how hydrogen is used throughout the study. Um, so if we want to summarize kind of the supply side resource mix that and options that are used in this AGA study, the first is geologic natural gas. So again, that's the the dominant form of natural gas today that continues to be used over time in these pathways in decreasing volumes as some of the renewable and low carbon gas resources come online in greater volumes. And so what are those other resources that we're using? So RNG, this includes both RNG produced from anaerobic digestion, as well as RNG from thermal gasification of a variety of different feedstocks. Then in terms of hydrogen, there's a few different approaches hydrogen is used in the study. So the first one is hydrogen blended into the natural gas supply. So assuming that a certain percentage would be possible to blend into existing infrastructure with minimal upgrade requirements. The second approach is methanated hydrogen. So, this represents, really increasing the available RNG supply or low carbon gases that can be blended without the same sort of volumetric limits of pure hydrogen. And doing this, by producing this RNG from a clean hydrogen feedstock that has been methanated with biogenic CO2 to produce again pipeline compatible gas. The third approach for hydrogen here is dedicated hydrogen infrastructure. So this would represent, the potential build out of new infrastructure that is accommodating 100% hydrogen in those pipelines. Again, a quick overview. I'm not sure if Ryan touched on this, but we're happy for people to put up their hands and ask questions as we go, and Morris and I can try and address those on the spot. So with that brief overview, we're going to jump into some of the RNG supply details. So Morris, I will turn it over to you here.
Thanks, Peter. So yeah, hello everyone. I'll just run through some of the sort of higher level context around RNG, and then sort of dig into some of the supply side estimates that we pulled together, both for the work we did a few years ago for the American Gas Foundation, our 2019 national report, and then also the more recent net zero study, and sort of how the supply side, the supply of RNG, the analytical approach have sort of evolved over time, particularly when we start talking about 2050 and net zero sort of pathways. So firstly, just a little bit of level setting for RNG. What we're talking about here is the pipeline compatible natural gas, basically, that is is equivalent chemically to geological natural gas, derived from biomass or biogenic sources. So it has a lower GHG emissions than the conventional natural gas. So in our supply side analysis, we look at 8 different feedstocks, biomass-based feedstocks that can produce RNG. Typically, these are coming from waste streams. So we're talking here landfill gas, wastewater, food waste, animal manure, residues from agricultural and forestry, and then also the last one is energy crops. And I'll just note that for all of these feedstocks, and we'll get into a little bit more detail later on, but for all of these feedstocks, we generally approach it from a pretty conservative point of view, just around the potential, the overall sort of biomass potential. And there's also sort of the input and the data that we use to estimate it, that there are limiting constraints around overall biomass availability. So an example might be for agriculture. we use the DOE's billion ton study as a starting point, and they already have in their modelling, they have limitations and constraints around you can't take every scrap of ag residue biomass from cropland. You have to keep some of it on to maintain sustainability criteria associated with the soil and sort of the functioning of sort of the crop and the land itself. So it's not like we're sort of getting every scrap of ag residue. Similarly for energy crops, there are those same sustainability constraints, and we're also not looking at land use change for energy crops. So we're only considering energy crops that are already sort of on land that is already considered agricultural land. And then in a lot of the cases, we're not actually seeing any land use change within the ag sector. So it's more once you impose a incentive, a price for the biomass to produce RNG, you start seeing energy crops growing on sort of inactive sort of ag land rather than say shifting from food to fuel sort of. So again, I just want to level set there so that we're not sort of saying that sort of half of the Midwest has switched over to producing energy crops or RNG, sort of away from sort of food crops and those sort of things. So next slide, Peter.
Morris, we have, I think, a first hand up.
Oh, okay.
Yeah, hi. I just wanted to expand upon that point about land use change. And when you say that if it were to come, it would come from inactive areas, is that to say that it's just coming from land that would lay fallow or land that may have been projected to be, housing developments down the road? Or can you expand upon that just a little bit?
Yeah, sure. So it's coming from the DOE billion ton study and their underlying land-based models. And so it's coming from land that they've already classified as being agricultural land. And typically it's sort of, particularly at the lower prices we're talking about, it is sort of fallow land and say pasture land that's not in high productive use. And then once you impose a price, then there's an incentive to say shift this fallow land to start producing energy crops. Now, that's not to say that within sort of their modeling construct, if you get up to high biomass prices, there's not some switching from, say, corn production to energy crop production. But in our approach, we generally don't go to those higher biomass prices, so we don't see a huge shift in a general sense. There's not a huge large scale shift from sort of productive land that's producing, say, corn, shifting it over to energy crops. In relation to, say, future housing development, it's not as prescriptive as that, as to say in the DOE sort of underlying modeling, like here's exactly what this land could be used in the future. It's just at the moment it's classified as agricultural land, whether it's being used for productive uses or not. So it's more that classification is the initial one. So that's not to say that in the future some agricultural land could shift to housing development, but we don't necessarily identify that as sort of we don't sort of look into those sort of broader macro trends within the within the modeling for energy crops. And I think I just saw another. So I think in relation to the prices, I think that's a good question, just around the motivating, switching over from fallow land to the production to produce energy crops. I think it's just in relation to, and it's just the economic construct of the underpinning modeling is just at the moment, say the land is not that productive for conventional agricultural products, but if you impose, say, a $100 ton price for the biomass, a dry ton price for the biomass, a farm gate price, that shifts the economic incentive so that this land is then sort of, I suppose, considered quote unquote productive, and that there is the potential for a different type of energy crop. So it's all sort of climate and geography based across the US. So that it just creates that incentive that is not otherwise currently in place around that there's not enough value generated from the potential crops that could be grown on that land. But if you have, if the biomass from the energy crop is valued highly in sort of a longer term time frame, that's where you'd see this shift from sort of fallow or unused pasture land switching over to energy crop production. And sorry, I see another question as well.
Hi, apologies if I missed this, but could you give some examples of what energy crops might be?
Yeah, so there's I think there's about off the top of my head, I think there's about 8 or 12. So there's like switchgrass, poplar, biomass sorghum, and they're all sort of again the modeling is detailed in the sense that it's geographically granular. And it's based on sort of the climate and geographic zone. So it's sort of if it's cropland in Texas or agricultural land in Texas, it'll be certain types of, I think, mainly switchgrass and those sort of energy crops. Versus if you get up into different northern climates in the US, that's things like poplar and eucalyptus and things like that are also grown. So sort of fast-growing trees, sort of small fast-growing trees as well. So there's sort of a relatively broad variety, and it's not necessarily assuming that all you know all like a single type of it's not relatively homogeneous in the sense that it's just one or two types of energy crops across the entire country. So okay, I'll just shift on to the next slide. So in the 2019 study that ICF completed, we looked at basically the resource availability for RNG feedstocks across those eight feedstocks I mentioned, and we sort of estimated a technical potential of sort of what is the entire, it was sort of an inventory of the biomass feedstocks that could be used to produce RNG, and we developed this number. It was a technical potential. And it was estimated at around 14,000 trillion BTUs across the US. And as part of that, the next step was we developed a couple of cases of applying different constraints to those different feedstocks. And we estimated a low and a high supply cases of applying these constraints. How much RNG could you sort of feasibly get into the pipeline with these constraints? And again, I'll get into these constraints a bit later on in the AG the net zero analysis. But it's sort of, for example, of all the landfills across the US, we're assuming that, say only ones over a certain size, only ones that are open or only closed recently. So that's sort of a bucket of RNG supply. And then we sort of say only, say, 50% of these landfill sites, facilities produce pipeline RNG. So we sort of apply these different layered constraints. I think the key point around this AGF work was these supply cases were not developed or framed around sort of specific policy objectives or GHG targets. It was more just sort of a national look at here's the amount of supply out there, and here's how the numbers sort of fall out if you apply these different constraints of if we captured X percent of animal manure, here's how much RNG you could get from the animal manure. And that I think is a sort of a key difference when we shift to the AGA net zero work, and to be honest, a lot of the other work we're doing around sort of economy-wide decarbonisation is just when we're talking about getting to net zero and how we're sort of pushing in all parts of the economy. We can sort of probably be a bit more aggressive around the RNG supply versus what we did in the AGF work. So moving on to the next slide. Sorry, so MSW is biogenic municipal solid waste, and WRRF is water recovery resource facility. So it's the new word for wastewater. Sorry about that. Yeah. So moving on to the next slide. So we developed a new supply case for the AGA net zero work, and it's characterized around framed around the economy-wide deep decarbonisation. So we're talking sort of net zero targets by 2050. And generally, when we've been working across sort of the economy-wide sort of how to hit net zero targets, basically what we're looking at is aggressive deployment of emission reduction measures across the economy. So I think that's relatively uncontentious in the sense that to hit net zero, you need to sort of pull on all the levers across the economy to reduce emissions. So we're talking, GHG-free electricity grids, comprehensive and aggressive transportation electrification, and also the aggressive deployment of low or zero carbon fuels across the economy. And not just with ICF's work, but we're seeing it with sort of other work as well. That there seems to be a renewed focus on the role that bioenergy can play as one of the measures that can help deliver on deep decarbonisation. So from this context, that's where we went back and looked at the AGF supply cases from 2019 and sort of reframed them around this aggressive, the more aggressive policy framework that we're looking at, and we ramped up some of the supply options and sort of loosened some of the constraints um, to capture more of the RNG supply, to make sort of RNG contribute more to the emission reductions. And this supply is sort of consistent and sort of reflects the sort of the all hands on deck approach to sort of the economy-wide deep decarbonisation. And I'll just note, so you can see the chart on the right, the column on the far right here has the high case of about 4,000 trillion BTU out of that 14,000 trillion BTU. And so then in this net zero case that we developed last year, we're up to nearly 7,000 trillion BTU. But again, that still reflects about, I think it's a bit less than 50% of the technical potential of the biomass feedstocks for RNG. So again, we're not assuming that every piece of biomass, every scrap of biomass across the US is being collected and directed towards RNG. It's still a relatively conservative approach in the sense that we're allowing for either biomass not to be directed towards RNG and sort of potentially be directed towards other biomass uses such as liquid biofuels, or it's not being captured at all as well. So Peter, I think the next slide.
And Morris, the last thing I'll just add here quickly is that the 2019 AGF study was focused on 2040, while the more recent AGA study was looking at 2050, so another kind of decade of development in there.
Yeah, no, good point. Yeah, we sort of framed it. It was sort of shifting out to the 2050. I see another question. Sorry, hand up.
Yeah, hi, this is Zach Baker with the Oregon PUC. Just had a question, if you could help provide some reference for the numbers that you're talking about, up to 7,000 trillion BTU. How much is that a percent of all of the natural gas, say, in the US, just to kind of put it in perspective?
Yeah, no, sorry. Yeah, no, that's good. Good question to sort of, those numbers can just sort of often mean nothing to people besides me who work on it each day. So I think national natural gas consumption, I think just off the top of my head, is about 15,000, 17,000 trillion BTU. So that includes power generation, residential, commercial, industrial, transportation. I think the numbers fluctuate year on year a little bit, but it's somewhere in that sort of 15,000, 17,000 ballpark. I think one marker that the AGF study we used was, I think, residential consumption and again, this is like a few years old now, 2018, I think it might have been. Residential consumption, I think, was about 4,500 trillion BTU, US wide. And so, yeah, like it sort of puts it in context that RNG, and I don't think we've ever sort of pushed this case, but RNG is not going to solve sort of natural gas consumption and reduce emissions. It's not the only solution, the final solution. It's more, it is just it's a piece of the solution that both supply side and demand side, and it's not going to solve. It's not a silver bullet. It's going to solve it all, but it is sort of a valuable wedge that can help sort of reduce emissions for contribute to sort of delivering the emission reductions across the natural gas sector, across sort of natural gas consumption. I don't know, Peter, if you had anything to add on that sort of that broader number.
No, I think that makes sense, Morris. I think you covered it well.
Okay. And I think another hand up as well.
Yes, thank you. Could you say a little more about the all hands on deck approach? What constraints you had to relax, or what assumptions you had to tweak? I get that it's 10 years further along, but is there a list of those assumptions that are relaxed?
I think on the next slide I'll sort of get into the details. Next couple of slides I'll sort of step through some of the constraints across all the feedstocks and then do a bit of a deep dive for animal manure.
Thank you.
So just for this slide here, we're just showing a comparison across the AGF 2019 high case and the new net zero case. So again, the starting point is that we're capturing, as I mentioned before, we're capturing about 48% of all available feedstocks in this new this new net zero case. So again, we're still leaving 52% of the available biomass is not being directed towards RNG, but it's broken out feedstock by feedstock here. So the dark blue column is the overall technical potential for that feedstock. So just focusing on animal manure on the right here, you can see that based on a livestock head count across the country, and if you captured all the manure potential from all of that livestock, the energy content of sort of that manure is 2,500 trillion BTU. The yellow column in the middle there is the supply potential that we used in the AGF study. So you can see about 18% of that technical potential we sort of assumed could be in that case could be directed towards RNG. And then the green column here is showing what the potential is in the net zero case. So for animal manure, it's 34%, nearly 1,000 trillion BTU of the 2,500 trillion BTU. So you can see moving along, there's the 8 different feedstocks, and you can see the overall potential is different for each feedstock in the sense that some have relatively minor contributions, maximum contributions, whereas others have significant, such as ag, residue, and energy crops. So you can see that across the board, we ramped up the supply potential for the net zero case. But again, for some of them, we still are not sort of approaching anywhere near maximum technical potential. I'll just note as well that we did, as part of this, we did push relatively hard on landfill gas. And I think there's a couple of some thinking there is that sort of basically when it comes down to it, there's not a lot of alternatives for landfill gas use, in the sense that the biogas itself obviously can be used for electric generation, but we're just sort of seeing the market shift away from landfill gas being directed towards on-site non-dispatchable electric generation. But basically, because it's coming out as a gaseous fuel, there's not a whole lot other options for it, in the sense that you're not going to convert it to liquid biofuels or other use. So that's where we push pretty hard on landfill gas. So you can see that we've shifted up from about 68% in the AGF work, the high case there, and we're actually capturing 93% of landfill gas. But yeah, you can see across the board there that we've ramped it up, but again, it's not maximizing. So for example, ag, residue, energy crops, we're still capturing less than 50% of the overall potential, and in particularly for energy crops, like we don't want to start pushing up to that 4,500 potential. We sort of apply those constraints so that we're not pushing really aggressive on those feedstock types. Just moving on to the next slide, Peter. I think we'll get into, okay, yeah. So this slide here, we're just focusing on how we get from that technical potential down to the actual supply we use in the net zero case. So as I discussed, the total technical resource potential, so that 2,500 trillion BTU, it's very much a bottom-up approach of basically counting the amount of livestock and the different type of livestock across the US, and having sort of the manure production rates, the daily manure production rates for those different animal types, and then the energy content of their manure, and you can get an annual estimate to sort of say, here's how much overall, like the energy content of the manure being produced by the animals. And so that produces that total technical resource. But then for animal manure, we applied a technical availability factor to this to each of the feedstock livestock types, and to say, basically the practical perspective of, not all manure can be collected and utilized for RNG production. So, for example, beef cows, beef cattle are dispersed in fields. You're not going to go around and pick up every piece of poo to sort of put in an anaerobic digester to produce RNG. So we apply different technical availability factors for each livestock type. So, for example, dairy and chickens have a factor of about 50%, because generally for chickens, they're particularly for sort of the large scale chicken farming, they're confined in the localized areas, in the sense that they're in sheds, and you can collect that manure, that a high proportion of that manure is sort of more feasibly collected, and you could direct it towards RNG production. And similarly with dairy, through the milking process and those sort of things, that there's a lot of manure is collected at those dairy facilities. So, and then, for example, for other types such as beef and swine and other animal types, there's a lower proportion. So about 20% of that manure can be collected and potentially directed towards RNG. So that's how we get to this, the middle circle here of the available resources reduced from 2,500 trillion BTU down to about nearly 1,200 trillion BTU. And so then from that point, we apply a different constraint for different scenarios. And so this is where in the net zero scenario, we assume that 75% of this available resource is directed towards RNG production. So again, we're not capturing all of the manure that we think could be feasibly collected. We're assuming only 75% of it is directed towards RNG production. And again, this is still relatively aggressive, but we're still framing this in the context of trying to get to net zero in 2050, and we want, we're assuming that sort of the entire economy is shifting. It's not just where we're pushing hard on RNG. It's sort of we're pushing hard on everything, whether it's electric vehicles, whether it's GHG-free grid, whatever else. And so then, just for context, in the 2019 high scenario for the AGF work, we assumed it was about 60%. So you can see we've ramped up from 60 to 75% of the available resource. And we could basically replicate this across all the feedstocks to sort of show how the constraints are applied and limit sort of the overall biomass potential that is directed towards RNG in the supply cases. And I think, I'm sorry, another question. Sorry about that.
Yes, hi, this is Pat DeLaQuille. This is a good story about your buildup of your supply, your resources, and your available supply. But where's the cost side of this supply cost equation? Because this is really what we're looking at. It's not a matter of what's available. It's a matter of how much it's going to cost as well.
Yep. I'll cover that on the last slide. We've got the cost component as well.
All right, thank you.
So Peter, on the next slide. So yeah, just to I think someone's earlier question around the constraints across the different feedstocks. So as part of the write-up of the net zero report, we go into detail across all the different feedstocks, but this table on the right here is just showing the key parameters. So I think for animal manure here, you can see that, as discussed on the previous slide, that we're capturing 75% of the available resource to get to that 867 trillion BTU. And as you go down, you can see the different constraints. So for food waste, we're relatively aggressive on food waste. We're capturing 95% of the food waste that becomes available at a price of $100 per dry ton of biomass. Landfill gas, we're capturing 95% of eligible landfills. So eligible here is, again, I noted earlier, it's sort of they're above a certain size, and they're also either open or recently closed, just in that the methane potential from landfills declines over time. So we're not sort of assuming there's old, smaller landfills, that we're not sort of capturing the resource potential from landfills. And we go down to wastewater as well. 95% of facilities that handle over 3.5 million gallons per day of water. So again, it's sort of restricting the sizes of facilities that we're looking at. And then just for the key parameter for the thermal gasification feedstocks, this is driven by the DOE's billion ton study, the underlying analysis there. But basically what we're imposing here, as I noted before, as you increase the biomass price, more biomass sort of becomes available. And so here we've limited it to $50. And so the DOE modeling goes up to $100 per dry ton. So here we're limiting it to $50 per ton. And then at that price point, you can see the percentages of that biomass that we're capturing across those price points. So for ag residue, when there's a biomass price of $50 per ton, we're capturing 80% of the ag residue that's available. And so you can see energy crops, we're capturing 60%, forestry, we're capturing 80%, and the types of biogenic municipal solid waste, we're capturing 80% at that $50 per ton. And you can see just down the bottom there, they've got the utilization percentage, so it's 45%. So again, we're capturing 45% of the thermal gasification feedstocks, and then 54% of the anaerobic digestion feedstocks. And so I think just lastly on the last slide, the cost assessment. So what, how we approach the cost assessment is it's the production cost assessment for the RNG. So it reflects the all-in cost to collect, clean, deliver the RNG up to the point of pipeline injection into a common carrier pipeline. It's purely production cost in the sense that we do not reflect environmental attributes associated with the RNG, such as when it's used in the transportation sector. This slide here, we haven't replicated it for the net zero work, but the slide itself is not particularly out of date in the sense that typically the cheaper feedstocks, the cheaper sources of RNG are coming from the larger landfills and larger wastewater treatment plants. So we're talking sort of prices, particularly for the large landfills, of less than $10. But then as we shift up the supply curve and we start bringing in animal manure and other thermal gasification feedstocks, that's where we see the price escalate to sort of above $20 per MMBTU. So you'll note here that the x-axis is only going to 2,500 trillion BTU, but again, this is from the AGF report. But if we extend that line out to to reflect sort of the 7,000 or 8,000, the 7,000 that we're looking at in the net zero case, typically we see it level out at around $20 to $25 per MMBTU, just because that's sort of the baseline cost for the thermal gasification production. In the sense that across those sort of ag residue energy crops, it's coming out at sort of between $20 and $25 per MMBTU. And again, we're not capturing in these scenarios, we're not trying to capture like the really high cost, small animal manure, small wastewater type facilities. We're assuming that we're not trying to capture those really high cost ones. We're still just trying to be relatively cost effective. And I'll also just note as well that like we often, particularly for RNG, like we focus on the dollar per MMBTU figures for the cost. And that's fair, definitely, around customer impacts on rates and those sort of things. But I think one key component that we're not jumping into here, but one key component we always try and keep in the back of our head is RNG is not necessarily competing with, say, conventional natural gas, but RNG is competing with or working with other GHG emission reduction measures. And that's where we just try and also think about the dollar per ton of CO2 reductions that RNG is delivering. And so just looking at these, when you convert these prices from MMBTU, like dollars per MMBTU to dollars per ton of CO2, there is just that, the cost effectiveness of RNG, particularly if we're talking 2040, 2050 in a deep decarbonisation framework, RNG can be quite cost effective over the longer term. It's more in the near term, there's sort of that sticker shock around the cost of RNG. But again, we try and sort of think about this more in the longer term, and also if we're trying to get to net zero. So I think that's the last slide I had. Was there any other questions on RNG before I think we shift over to hydrogen? Yep.
Hi there, Kara Saylor from the Green Energy Institute. Do you mind going back a few slides? Sorry, it's afternoon, and so I may have just missed this, but the one that shows technical potential, the 2050 study, and then I think it showed your 2019 study. It was a chart. Yeah.
Yep.
Can you just dig in just a little bit more? And again, apologies if you already covered it. What changed between the 2019 study and the final 2050 study?
So the 2019 work, basically what we did was we just loosened the constraints a little bit for each of the feedstocks. So again, to focus on animal manure, what we did was so that the orange bar here is capturing, I think 60% of the technical of the available resource. And we loosen the constraint to say it's 75% of the available resource. And so we just loosen those constraints. The underlying sort of data set, and that sort of relates to the dark blue columns here, they didn't change across the 2019 AGF work to the net zero case that we developed in the 2021 work. So the blue columns didn't change. It's more we just changed the constraints to push more aggressively across those different feedstock types. So another example is the landfill gas. The 3 columns there, you can see in the orange yellow high case from the 2019 work, it's 68%. So it's probably looking at, off the top of my head, I think it was we're capturing about 75% of eligible landfills. And then the shifting to we loosened that constraint and sort of said, okay, we're going to capture 95%. And so just related to, I think, Tim Miller's question here is like, but on what grounds? I think, again, what we're trying to frame here is that we're not being prescriptive around sort of the policy and regulatory framework to say, here's what policy or price or whatever else you need to get this much RNG in the pipeline. What we're taking a step back here and saying, if we're pushing hard everywhere across the economy, we are going to apply less conservative restraints on this RNG supply, in the sense that for the landfill gas, if in 2040 or 2050, this is going to, we need more resources across the board, and so we should contribute, and like landfill gas should make a more aggressive contribution to hitting, say, a net zero target. So we're not necessarily being prescriptive to say, here's how the market will change. It's more of in a general context, we need to be pushing aggressively on all of these different biomass-based feedstocks, combined with the pushing more aggressively across everything, in the sense that, no more internal combustion engines will be sold from 2035, or there'll be no, everything on all the electricity will be GHG free by 2040. So it's sort of in that context of getting to net zero, it makes sense that we should push harder, say, for example, on landfill gas. So yeah, sorry, there's another hand up. I'll just answer.
Yeah, thank you. It's Pat DeLaQuille again, and following up on this question as well. If you look between these two studies, what was if you can give us a general answer, what was the general impact in terms of the cost? Because again, you're going to ramp up supply, you're going to require additional effort on the part of various producers, and et cetera, and those are going to result in a higher cost. Can you give us a sense of what the cost impact was from going from the 2040 to the 2050 results?
Yeah, so like the cost component, and I think that's again where we did a relatively conservative approach for cost, in the sense that the cost is more of a snapshot of the costs at the moment for RNG, and so I think while we move up the supply curve to capture more of the RNG in the new case, we're also and so, but as I noted, there's a pretty flat element of the supply cost curve, in that because there's significant volumes of thermal gasification feedstock, so ag residue, forestry residue, and energy crops, the cost remains pretty static at around $20 to $25 per MMBTU. So a large wedge of the supply cost curve sort of sits around at that price, and then it sort of, as you get up to the tail end of the smaller animal manure and say smaller landfill gas facilities that we might want to tap into, that's where the price approaches $30 per MMBTU. If we're talking sort of the national supply of around 7,000 trillion TBTU. But again, the average weighted cost, typically we're coming out at sort of between, not to focus on decimal places, but it's sort of around $22.36 or $23.12. Like when we sort of layer in all the different the cost, the feedstocks that build up that supply, it bounces around between that $20 to $25 per MMBTU cost range. And again, I'll just note that we haven't laid in any cost reductions or any efficiencies around the production costs that could eventuate, particularly as we're going from national supply of RNG is about 70 or 80 trillion BTU sort of in 2021. So if we're increasing that to 7,000, there is the potential there for cost reductions across sort of the production process as well as noting your point that like we're also capturing potentially more marginal feedstock sources. So I think there's two pressures there of like there's the potential for costs to increase, but I think there's also the potential for production costs to decline as well as we ramp up supply.
And just to be clear on what Morris has been outlining here, I think he's been giving you his perspective on how this 2019 cost curve, or this cost curve from the 2019 study, might shift with a larger supply mix. But we should just be clear that the recent AGA study did not include kind of reporting on costs of pathways or costs of RNG. So the reason this kind of context on RNG cost is using the 2019 studies curve is because there wasn't a formal assessment done on the cost curve for this expanded RNG potential. And I think some of the other questions have been addressed in the chat already, just in terms of how these costs do include assumptions for interconnection and compression and so forth.
Okay, unless there are no other questions, Peter, I think I can probably hand over to you to get into the hydrogen.
Perfect. So in terms of what was done in the AGA net zero opportunities for gas utility study, first, just to kind of highlight some of the differences for RNG relative to hydrogen that we're not talking about. So in Morris's discussion just now for RNG, we were really focusing on the key limiting factor for RNG as the feedstock potential and and what can be produced. And we've also talked about costs, which would be a factor in how much RNG gets used, and potential competition for RNG. But as opposed to that RNG approach where we did a detailed analysis of the available supply, for hydrogen in this study, this study is not like a detailed analysis of the total potential hydrogen that could be developed in the U.S. So what we're really focused on here in this study is kind of constraints or limitations on gas utility customers' ability to use hydrogen and acquire hydrogen. So we're really assuming whether it's green hydrogen or blue hydrogen or other forms of clean hydrogen, that there could be as much hydrogen, clean hydrogen, produced as would be needed. And that was something that the working group on the study was generally comfortable with. The exception to that is methanated hydrogen, and we'll talk about it a bit more in a second. But there we suggested that the amount of methanated hydrogen could be limited by the availability of biogenic CO2 to actually methanate hydrogen, and so we applied some constraints based on that. In terms of and then in terms of other constraints on just the constraints on use, we already talked about how there's blending limits, and those are some of the key kind of parameters that we are looking at in this study. Again, costs for these types of conversions, whether that's retrofitting existing infrastructure or the hydrogen supply costs, are definitely going to be relevant, but we're not a focus of this. We're not a focus of this study, which again is more showcasing different pathways that could be used, and not trying to answer what is the optimal pathway. So this slide lays out a little bit more specifically the different approaches that the study uses. So again, we've kind of touched on this. The first one being hydrogen blended into the natural gas supply. The second one being hydrogen that's methanated into synthetic renewable natural gas and blended into the natural gas supply. The third approach here, it would be kind of clusters, hydrogen clusters for industrial or power generation customers to access 100% hydrogen through networks that supply that. The fourth and fifth are conversion of buildings, so residential or commercial customers to 100% hydrogen, which is contemplated in one of the studies for four scenarios towards the closer to 2050. And just acknowledging other approaches as a sixth, so not other things we looked at in the study, but certainly there are a whole range of discussions on how hydrogen can be used and distributed, and so definitely would not limit the possibilities to what we looked at in this study. So in terms of the first approach there, blending hydrogen into the natural gas supply, what we used in this AGA study was an upper blending limit of 7% on an energy basis, which is equivalent of 20% on a volume basis, as the hydrogen is less less dense energy content, and we're getting up to that level by 2035. There are a lot of gas utilities out there who are kind of piloting and trying to explore ultimately what blending limits will be possible, without significant infrastructure investments in their systems, whether that's higher and low or lower than these levels. But these are relatively commonly used upper thresholds from decarbonization studies. I should note that when we're talking about 20% by volume, it's typically a distribution level number, while sort of the same kind of core sources or study from a while back that came out of NREL would have pegged kind of the transmission pipeline blending level to be closer to 50%. So yeah, I should also note, that not all of our scenarios in the study went up to that 20% level, but again, we were focused on demonstrating a diversity of approaches. So some of them went up to the level, and at least one of the scenarios used a lower level of hydrogen blending. So the next approach that we included was methanated hydrogen. And so, here again, we're producing a pipeline compatible form of methane that is being produced by combining clean hydrogen with a biogenic source of CO2. So really, it's functionally equivalent to renewable natural gas, and in many ways it kind of adds to the available renewable natural gas supply. But we kind of counted it separately from the RNG to kind of reflect and capture the fact that it was being enabled by the availability of a clean hydrogen feedstock, essentially. So I noted a little bit before that we limited the availability of methanated hydrogen based on the availability of kind of carbon neutral CO2 that could be used in that methanation process to, again, make sure that this methane that was being produced could be considered renewable. And so, we talk about in the study how there are a variety of different sources of biogenic CO2 options that could be available. Sometimes that's biogenic CO2 that's coming off an ethanol plant or some other facility of that nature. But in this study, we pegged the potential for methanated hydrogen to an assumption that this could be paired with thermal gasification processes for renewable natural gas, which actually do already include a methanation step. And so thermal gasification RNG processes also have some CO2 waste streams that are, not typically captured because there's not enough kind of hydrogen coming out of the gasification process to combine with all the available biogenic CO2 and produce that RNG. So again, here the assumption is that if we were able to, add clean hydrogen in combination with these thermal gasification RNG production facilities, we could essentially double the RNG produced by thermal gasification. And so, we've taken a look at some of the chemistry on publicly available data related to kind of the flue gas streams from thermal gasification, and this can vary significantly, or can vary at least a bit by process. But the available biogenic CO2 from those processes suggests that it could be possible to between triple or quadruple the RNG output through hydrogen addition, or at least that there would be enough CO2 available to combine with clean hydrogen. That being said, it definitely will get harder and more expensive to kind of capture and utilize all of that available, or all of the CO2 produced through those processes. So there's definitely a trade-off there. And I should note that other kind of decarbonization studies that have been done, sometimes use CO2 from direct air capture or direct air carbon capture to as part of this sort of synthetic RNG fuel production, and so beyond biogenic CO2, that is one of the things some studies consider, and that would also be potentially an option, although is typically thought of as a more expensive approach to actually producing synthetic fuels. I think there's a hand up.
Yeah, thanks, Peter. Kara Saylor again from Green Energy Institute. Could you just explain to me a little bit more what the climate benefit of methanated hydrogen is? Is it this idea that you, as you were saying just now, CO2 capture systems capture, and then it needs someplace to go? What are the life cycle emissions, I guess?
So I guess the main point is just that there are different processes, whether it's ethanol production or even some thermal gasification RNG production, that releases some level of CO2 still to the atmosphere that's considered carbon neutral. It's biogenic because it's just CO2 that was captured by plants that is being released back to the atmosphere. And so there are potentially some biogenic CO2 sources of that nature, which could be combined with clean hydrogen sources to develop, to again sort of just increase the available fuel supply of renewable gases that could be leveraged in pursuit of decarbonization objectives. So it's really another approach to increasing the available decarbonized gas supply that is available. And in terms of other benefits, one of the key things here is that if you've blended a certain amount of hydrogen into your gaseous fuel mix, you can hit this upper limit we were talking about previously, that would require, otherwise require, significant upgrades, whether that's to the system or customer equipment. And by having, additional RNG of this nature, you can kind of utilize clean hydrogen, but bypass some of those potential transportation limits.
Okay, and I guess a follow up, and again, forgive the ignorance here, but when it burns in the home, is it the same? Does it produce the same amount of emissions as natural gas? Is it cleaner? Is that the idea?
So it would be the same as renewable natural gas, which again, when RNG is combusted in a home, it is essentially the same as geologic natural gas. And the IPCC and others consider it carbon neutral when it is coming from a biogenic source, and so it's considered circular in that nature.
Totally get that. RNG makes more sense to me. Methanated hydrogen, I'm trying to get my head around what the climate benefits of it are. And it sounds to me like it just essentially supports the use of RNG. If you don't have enough RNG, you can supplement with methanated hydrogen.
I guess the thought is that if you're able to produce enough kind of clean hydrogen with little or no emissions, and then you have these biogenic sources of CO2 that would otherwise be going to the atmosphere anyways, you can capture, utilize that CO2, that biogenic CO2 with this hydrogen, and essentially, you've removed the emissions from one place, and that emission might be happening in the home, but you've kind of overall haven't increased emissions at all, and so it's still better than having released that biogenic CO2 from this ethanol plant or elsewhere, in addition to burning gas, geologic gas in a home. So you're kind of going from 2 releases of CO2 to down to 1.
Okay, thank you.
Pat, did you have a
question? Yes, thank you. Pat DeLaQuille again. I'm more interested in the energy penalty. We're starting with electricity, let's say clean electricity, but then you're going to turn it into hydrogen, and you're going to turn it into synthetic methane, and let's say use it to heat a building compared to using that electricity directly. What is the energy loss in terms of energy delivered from that original energy source? I think it's fairly significant.
Yeah, so again, that's going to depend whether you're using, green hydrogen, blue hydrogen, or something of that nature. But with green hydrogen, you would have a significant loss, and so in this study again, we're not kind of claiming that anything is in all cases going to be an optimized approach. We're trying to showcase a diversity of pathways, and ultimately net zero is a really challenging target that may require a lot of different solutions, and you may find yourself with different pathways contemplate, for example, an overbuild of renewables, or having excess generation at different times of the day that may not be possible to store in batteries for the evening or something of that nature. So it's challenging to say that there is no role for something, even if it is not the optimized approach for everything, I guess. Because yes, there will be significant efficiency losses in electrolysis.
Yeah, and just to chime in there, a lot of the near-ish term, as you'll see from our cost perspective, this is Ryan, Pat with North Natural, of course. It's power that is, it's excess power, so it could potentially be put into a battery or some other form of storage on the electric side as well. But there's an efficiency loss, of course, associated with that as well, and also time components for certain technologies. With methanated hydrogen, it becomes a 1-for-1 replacement for geologic natural gas, which is cost effectively stored with resources that already exist today on our system. So you need to look at the entire life cycle of all of the options to get a good cost estimate. But again, we're not in a policy making process here. Some of those broader questions that touch so many systems we think are important, but this is focusing on specifically planning resources to meet our customers' needs in this process.
Yeah, I think
Yes.
that's.
Thank you.
Yeah, definitely the seasonal storage element is an interesting challenge that could be of relevance there.
Yeah, I mean, I think there are two different issues here. One, for storage and reliability issues, definitely hydrogen has significant advantages, but I would question whether heating buildings is a good use for hydrogen. personal opinion.
And again, I think it's a complicated question to answer when you have to look at a range of factors and consider what peaks of electrification mean and how electric infrastructure build out is required if kind of shifting primarily to that system. But again, it's not was not the question we tried to solve, I guess, in this AGA study. I'm just a bit over time, so I'm going to try and quickly go through these last two slides. I think that shouldn't be a problem. But just quickly in terms of dedicated hydrogen infrastructure. So in the AGA study, we included different levels of 100% hydrogen use in the industrial sector. In all of the scenarios, and then we had one of our scenarios that was contemplating, starting in 2040, some homes converting to 100% hydrogen and or new construction homes using 100% hydrogen, and in 2045, some existing buildings potentially converting. Again, that was just done in one of the studies as part of our approach of demonstrating a variety of potential opportunities, and something that's being studied maybe a bit more closely over in the UK right now. And then the final note I have here, again, people really like to focus on what type of hydrogen we're using. In general, in the AGA study, we tried to focus on clean hydrogen, and we weren't really, again, in the same way we weren't developing a detailed analysis of the hydrogen supply potential. We didn't do a detailed analysis to kind of come up with the perfect hydrogen supply mix. That being said, part of the AG analysis was a look at upstream emissions, and so for that analysis, we did need some assumptions on where that hydrogen was coming from, and so this kind of highlights those assumptions used primarily for that upstream assessment, with gray hydrogen currently providing most of the hydrogen that's used today, but a need to shift away from that as hydrogen starts to become deployed for the purposes of reducing emissions. Here we get to 75% green in 2050. So that kind of sums up the slides we had for folks today. Not sure if there's more questions on the hydrogen stuff. Any last questions on the RNG stuff, or Ryan, if you need to kind of cut us off, kick us out, and move on to the next topic.
We are happy to have you guys hang. I know that you are quite busy, so if you need to go,
I'm fine.
You can tell us that. But if there are any more questions, folks, feel free to, if Peter and Morris are able, if there are any more, that's fine. Okay, well, I want to, from all of us, thank you all very much for the information. It was a great presentation. I think that we all learned a lot from it, and we hope everybody can take a look at the full report. It's really great work, and as this market continues to grow, anticipate more and more research in this field. So with that, Peter, Morris, feel free to hang out and then if you want, but if not, appreciate it again. And what we'll do now is we're going to send it over to Anna from our renewables team and talk about how one of the reasons that we wanted to bring the ICF team in today is, we're very active participants in the renewable space. So we're actively getting a lot of RNG resources and trying to understand the broader market. And this really aligns with what we're seeing in the market and some of the prices. So putting that broader national context into perspective and what that means for how we're going to plan for our resources at Northwest Natural. And I will talk about the great work that we're doing there and give some insights about what we're going to be dropping into the model relative to cost and availability. So Thank you again, Peter and Morris, and Anna. I'll throw it over to you if you want to go ahead and share. It might be easier for you to drive, or I can if you want. Either way, you let me know.
Yeah, why don't you actually, if that would
Okay.
work. Great.
I can do that.
Thank you. Yeah, thank you, Peter and Morris. That was really helpful. Hello, good afternoon. I am Anna Chittum, and I'm the Director of Renewable Resources here at Northwest Natural. What that really means is that our group is the group that is going out into the market and working to procure RNG and renewable hydrogen. And so I'll talk a bit about kind of what that looks like. That is both us going out into the market and buying resources from existing projects, and then also getting involved in project development. So I'll also talk a bit about that. And yeah, please feel free to drop questions in there. I'll try to maybe pause occasionally and look over and see what we've got. So yeah, Ryan, can you go ahead and go to the next one? Thank you. So I wanted to kind of just step back a little bit because I think when we're talking about RNG and we're talking about hydrogen, there's all these different sources, there's all these different processes that in the end yield a gas that can be used and that is produced or captured in a way that offers a climate benefit. And so I think when we're thinking about how we reach our own carbon neutrality goals of 2050, how we think about reducing emissions throughout our service territory for our customers, we're really thinking about, what are the different waste sources that are out there? What are the different renewable sources that are out there? And then how can we process them in a way that they can meet existing customer needs, utilizing our existing system? And so that's really kind of what this image represents, which is that, as you heard, there are all these different sources of potential RNG. And so we're looking at, wastewater treatment plants, landfills, a variety of different waste streams coming out of the agricultural sector. But then we're also looking at low cost or excess renewable electricity or waste CO2 resources. And then we're thinking about how can we most cost effectively use all of these energy resources and then store them for when we need them. And I think that's one of the really critical things to think about when you're thinking about any sort of a renewable energy resource. If you can make it a gas, your options for what you can do with it and how you can use it to meet customer needs, how you can store it, they're much wider. And so that's really one of the driving factors behind how we think about decarbonizing our whole system. So if you can go to the next slide. Just to kind of level set for people who might not live and breathe RNG every day the way that my team does, renewable natural gas is really, and ICF talked about this a bit. I think someone has a dog in the background if they could mute. So renewable natural gas is really pipeline quality gas. So it means that, all of those different waste resources that we're talking about, as long as you can capture it and you can clean it and you can make it a pipeline quality gas that can meet our existing quality specifications that all of our other gas has to meet, it can be RNG. And so every utility, when they take gas onto their system, they're going to have a slightly different definition of what pipeline quality means. And that's really going to depend on their own system. It's going to depend on how old their components are. It's going to depend on what kind of gas they're buying from different resources. So for us, RNG onto our pipeline means that it is at least 97.3% methane and that it has at least 985 BTUs per standard cubic foot, singular. And so the sources that it can come from, as we heard about, lots of different sources there. You've got a lot of organic material breaking down in different places. And if you can capture it, and if you can, find some type of a scale, then you are likely to be able to generate RNG from it. So a lot of biogas resources that are being repurposed, expanded to allow more processing of wider varieties of wastes and to really be able to meet some of these some of the needs that we have on our gas system today. And I think that's kind of one of the prevailing themes about RNG is that there are all these different kind of disparate gas sources, gas that might be, maybe a little bit is captured at a wastewater treatment plant to run a genset, but a lot of other of that gas might be flared. Same thing with, certain animal manures. You might have, some that has been captured, but typically once you start thinking about renewable natural gas, it kind of brings a new perspective to a project because it's really driving whoever is developing the project to think about how do we capture all of the waste gas that's out here? How do we really make a efficient and a cost-effective project? And so in a lot of cases, RNG developers are coming into, say, a landfill that has captured some of its landfill gas and really thinking about how can we optimize gas collection at this landfill? Maybe there's still a lot of methane that's being emitted because of the way that the landfill's operating. How can we make sure that there aren't as many leaks happening in the landfill gas pipeline and stuff like that. So it's really an economic driver to capture a lot more than is out there is something that we kind of continually see in the RNG space. And I think the other point that's really critical to make is that once RNG is in the pipeline, it is fully interchangeable with conventional gas. And so just like if there is a variety of different renewable electricity resources going into a main transmission system, you at your home, you're not going to know exactly how much power at a given point came from this one wind farm or came from this natural gas power plant. But you can kind of look broadly and see, well, what's the general collection of sources that my utility is using. And that's similar with RNG. And we'll talk a little bit more about kind of how you track the environmental benefit of a molecule or a therm of RNG. Next slide, Ryan. So when we talk about RNG resources and projects in particular, which I'm going to talk a bit about, what we're really talking about is there's some source, there's some feedstock, and there is some type of a process through which a raw biogas is made. And so that could be an anaerobic digester. So that's what you're going to typically see for wetter feedstocks. In a landfill, you don't actually have a standalone digester. The landfill itself is really the digester. So the landfills are capped and you have little wells that are drilled into the landfill and the gas is captured out of that. So you've got a lot of different sources of raw gas. And then you take that gas and you run it through what we call cleaning and conditioning equipment. And there are really kind of three major types of equipment out there. And there's various benefits and drawbacks to each one. But there's kind of not one particular type of equipment that you use, but nevertheless, depending on kind of what the input is, you select an equipment or maybe kind of a series of pieces of equipment, and then what comes out is what we refer to as RNG, and that's really the pipeline quality gas. And so then at that point, again, it can be used for whatever natural gas is used for. So it can heat buildings, it can go to a CNG station to fuel vehicles. Again, kind of it can go to a power plant. It can really do sort of whatever natural gas does. And if you go to the next slide, want to talk just a little bit about all of this activity that's happening today. So all of the procurement and all of the project development that I'm going to be talking about, that those, the previous slide, I just kind of mentioned all this equipment. And so, there's a lot of reasons why both gas utilities and RNG project developers are investing in that equipment in order to produce RNG. And that's really kind of this policy environment that I'll talk about. Thank you. I found a typo. It says Oregon Senate Bill 89, but it's 98. So that's what that first bullet point is actually supposed to be. But maybe I'll pause because I saw a question from the audience.
That for me?
Yeah.
I just, this is actually a comment that the executive order that the Oregon governor did included landfills as one of the things being controlled, and they just adopted the rules last fall. So now's a good time to go hit up the landfills.
Yeah, thank you. Yeah, it's definitely, we have found that there's a lot of interest in how to, yeah, kind of maximize the gas capture from Oregon landfills for sure
Yeah, but I mean,
recently.
it's now included as regulatory that they have to do it.
Yeah, yeah. Yes,
That's why I
that's
thought,
definitely been.
that's why I thought I'd mention it here.
Yeah, thank you. Yeah, that's definitely that's been important for landfills to be thinking about what are they going to do with their gas. I also see a question, I think, from Kara.
Yeah, sorry. Thanks, Anna. And it just let me know if this is later in the presentation or too much detail, but curious about sort of the ebbs and flows, how reliable is, so just looking at your diagram from the previous slide. I guess I also wondered, is this when you're talking about a capped landfill, does that mean it's no longer accepting new? Does it have to be a closed landfill? Anyway, just curious about some of those kind of details.
Sure. Yeah, those are really good questions. So to your first question, the ebbs and flows, it really depends on the feedstock. So if you're talking about like a large wastewater treatment plant, um, the actual available organic material that yields biogas, that doesn't vary too much. The water itself varies because when it's a lot rainier, it's processing more gas, but ultimately what we're flushing down the toilets is pretty steady across or across the year. When you're talking about like a dairy or an on-farm based digester, you do see some variation. There's variation related to temperature. So you tend to produce more gas out of digesters when the weather is warmer. Gas production definitely goes down a bit when it's colder out. There's different ways to heat digesters, and everyone kind of has their favorite technology for doing that. But that's also going to be really dependent on the overall, ups and downs in production at the dairy or the agricultural facility. Landfills have probably the easiest to predict gas production curves. And so every landfill has these, basically they're like 100-year curves, and it's really just based on the amount of waste going in and waste in place. And so there's a whole kind of complicated calculation of how much gas you're going to have, you know, 2 or 3 years down the line based on what the waste going in today. So most landfills have that, and that's what we and others rely on. But then to your point about the capping of landfills, so most landfills are large enough that under EPA regulations, they have to do some controlling and gathering of their methane. In most cases, the easiest way to comply with those types of regulations is to just flare the gas. So you can't just have a fully open landfill anymore if you're over a certain size. That's actually illegal. So what we're talking about mostly is open landfills that as they complete a cell, which is like a hill in the landfill, they complete a cell, they kind of cover it up with this plastic. They might put they might drill some wells in there, and then they're going to start filling up a new cell. And so they're open landfills typically that are still accepting waste that will often have 10, 20, 30-year contracts with various haulers to accept waste. And those are really the most attractive RNG resources because you can have a pretty good sense that the gas production is going to be consistent and likely increasing over time as projections of waste increase. And I think it's good to note that we were in our first contracts for RNG really as of this year. And those are a variety of different sources. I'm going to kind of get into what those are. But we're really learning from those kind of what those ebbs and flows are going to look like. But it's a really good question, and definitely something that, like I said, it's very much related to the type of RNG resource. All right, I will actually, can you go back again? Sorry. So just wanted to kind of quickly talk about the policy environment for procuring RNG. Can't believe I I put 89, put that backwards because Senate Bill 98 is my life. But so in Oregon and Washington, there's a couple of policies that are and frameworks that really drive us to go procure RNG, why we're out in the market procuring RNG. The first is Oregon Senate Bill 98. So this was a 2019 bill that established volumetric targets for RNG procurement. And so for large customers, sorry, large gas utilities. So that has been the bill that we have been really driven by to go and procure RNG for our customers. And I think an important point is that this is RNG that we're delivering to all of our sales customers in Oregon. So it's not just, you know, customers that opt into it. We are working to decarbonize all of the gas that we're delivering to all of our Oregon sales customers. So in that respect, it's more similar to like an RPS on the electric side, where you're decarbonizing the whole portfolio. And then the Oregon Climate Protection Program. This is the recent program that the rules were just finalized, and for that program, that has RNG and hydrogen that is essentially it's going to be a framework that kind of drives us to procure even more RNG and hydrogen probably than above and beyond what we would acquire under Senate Bill 98. And obviously there's other ways to reduce emissions that can be used for compliance in the program. And so RNG and hydrogen are going to be an important part of compliance, but there's going to have to be kind of a broader look at what's the most cost-effective way to comply. And that's kind of a whole other conversation around sort of all the different ways that you can comply. But we do expect that that will drive us to procure more RNG and hydrogen, probably above and beyond, again, the Senate Bill 98 volumes. And then up in Washington, House Bill 1257 was passed, I think, also in 2019. And that, kind of similar to Senate Bill 98, it does establish a framework for bringing RNG to all gas customers in Washington with some caps. That is a kind of a pretty early, we're in sort of the early stages, I would say, of getting some RNG to Washington customers, and I can, you know, talk a bit more about that. But the other thing that House Bill 1257 does is it requires gas utilities to offer a voluntary RNG tariff. So that is something that we are just kind of getting in place in Washington. And then similar in terms of kind of a statewide climate cap, the Washington Climate Commitment Act also sets an emissions cap that we also expect will drive us to procure more RNG and hydrogen in Washington. And I think just the other kind of overall framing is other types of access to RNG that our customers are asking for. So for instance, we have large commercial customers who are really interested in using RNG above and beyond what we are already providing to them under Senate Bill 98. So we're building out some options there. So essentially kind of all of these things drive my team to go out into the market and try to get the most cost-effective RNG that we can. And maybe go to the next slide. So like I said, kind of the main thing driving us is really Oregon Senate Bill 98 and the procurements and investments that we've made to date. We have really done under the auspices of Senate Bill 98 and working towards the volumetric targets that that bill sets up. And I think, you know, that bill has its own definition of RNG. It talks a lot about, and it's not just the bill, but the final rules talk a lot about you know, what types of equipment we can invest in, how we go about procuring RNG for customers. So there's a lot of rules and framing around that. It does set a spending limit in order to protect customers, and so it caps at 5% of our annual revenue requirement. That's the amount of incremental cost we can spend on RNG, which really means the cost of RNG above and beyond conventional gas. And after I talk a bit about how we're going out and procuring RNG, Ryan's actually going to talk a bit more in depth about how we think about that incremental cost. And so I'm sure there's probably some questions around that, but I would say maybe hold those until Ryan talks, because he's going to give us a lot more info there. Ryan, can you go to the next slide, please? So when we're out and about trying to find the best RNG deals in the country, one thing that has been just really helpful, I think, to the market is that the number of projects that have been built, the amount of RNG that's available, we've really seen grow significantly in the past several years. Really the past kind of 5 years. I mean, if you looked at this map, even really about 5 years ago, I think there were maybe something like 55 or 60 operating facilities in the country. And so there's been a really significant growth in RNG facility development. And that has really been driven by policies at the federal level and at different state levels that are that lay out clean fuels programs, especially for transportation use. And so actually that's driven a lot of RNG. But what that's really done is kind of help the industry mature a lot. And then at the same time, you've seen more and more gas utilities looking to procure RNG, commercial and industrial facilities. So there's really been a big demand for RNG resources. And I think it's really allowed developers, allowed investors who are looking to invest in renewable energy projects, it's allowed them to feel comfortable bringing these projects online. So here in Oregon, there are 3 projects physically connected onto our system, and then there's several others that are outside of the Northwest Natural System but interconnect into other gas systems in the state. And so we've been, working to physically interconnect those projects, but then we've also been working to procure RNG for Senate Bill 98. And I'll talk just in a little bit about, where we're buying that RNG from. But really, we're kind of looking about the whole country, and we're trying to identify the most cost-effective resources for our customers. We're getting RNG from different places, much like how we get our conventional gas from lots of different places outside of Oregon. So we've been pretty busy in the last couple of years signing a number of contracts and development agreements. And right now we have about 3% of our Oregon sales volume under contracts that are either set to deliver, or they give us options to procure. So just in the past couple of years, we've gone from 0 to 3%, which has been, we're pretty proud of that, but there's a lot more room to go. And so that's why we're really busy going out and procuring. Ryan, can you go to the next slide, please? So I mentioned earlier that I was going to talk a little bit about, how the actual RNG transactions occur. And I think a good framing of this is thinking a bit about how the transactions occur on the power side. And so I'm going to use a term, RTCs, which is Renewable Thermal Certificate. And that's actually it's a term of art that was defined within Senate Bill 98, but then it's been used in a number of other policies, and then also the main the protocol for for trading and tracking the environmental attributes of RNG uses RTCs as well. So RTCs really is the environmental attributes, it's the environmental benefit of RNG, such that you can kind of separate that from the underlying gas, much the same way that you separate a wreck from the underlying electricity. And then that RTC can be transacted. And so when we talk about a bundled source of RNG or a bundled price for RNG, we might be talking about buying 1 decatherm of RNG that kind of depending on where it is might come as the gas and the attributes, or it might be that the attributes and the gas are separate, and the RTC is essentially reassigned to a decatherm of energy that's used. And I'm not sure if I explained that very clearly, but again, if you go to the next slide, that might help. Very similar to how the transactions for renewable energy certificates occur on the power side. So it's really kind of the definition of the environmental attributes are in that RTC. So once an RTC is generated, the underlying gas, then we don't claim that as having any environmental benefit. It's just interchangeable with conventional gas. And I think, you know, I mentioned this protocol, this tracking protocol. MRETS, which is the Midwest Renewable Energy Tracking System, they're the entity that has historically tracked RECs in the MISO market, which is the mid-continent. I always want to say Midwest, mid-continent independent system operator. So they've done that for years with RECs, and they just happened to be the first entity that recognized that this RNG market was growing, and there was going to need to be some type of a tracking system for the environmental attributes of RNG. And so MRETS really was first out of the gate with a whole kind of protocol and framework around tracking and documenting RTCs and really making sure that they're not double counted in any way, and that if you're using them to retire on behalf of customers in Oregon, no one else along that value chain is also claiming that. So I think it's really important because we rely on that. We have our accounts on MRETS, and we really make sure that any producer that we work with is comfortable registering and moving their RTCs on MRETS, and that's really kind of our source of the truth for what we are delivering to customers. Next slide, please. So there's a lot of different ways that we go about procuring RNG and evaluating projects for development. So I'm just kind of spend some time talking about, what that looks like and what we do. And ultimately, kind of no matter what the RNG resource is and how we have found it, how we have procured it, we really try to compare them on an apples to apples basis, which again is Ryan will go into a little bit about how we really do that. Because RNG resources come to us from a lot of different ways. So we run an annual RFP process for RNG resources. We've run 2 so far. We're actually going to release our 3rd RFP in a couple of weeks here. We really push that out far and wide. We try to get all sorts of developers and owners of RNG resources excited about selling to a utility. I think one interesting space that we play in the market is we can offer long-term fixed price contracts, and that is very different from historically what has driven the RNG market, which has been much shorter term contracts tied to these transportation fuel markets. Those markets have been very, very lucrative, especially recently, but they're very volatile. So if you put your money into developing a project, it's possible that you could get that entire project paid back in 2 years, or it's possible that it's going to take you 15 years. And it kind of depends on what those markets do. So we're able to operate in that market and say, we're not going to probably pay you per MMBTU the amount that you're going to get in these other markets, but we can offer you this reliable, 10, 15, maybe even 20-year contract for this resource that you can bank on. And that's been really important for, I think, the growing maturity of the market. So that's our that's kind of our invitation to the market is to, pitch us your resources, tell us where they are, what the feedstocks are, who the owner is, and then they propose their prices and their volumes. And we do kind of a set evaluation of the resources that come through our RFP. And then we also do a rolling evaluation of other offtakes, because there are just some projects that they might not be ready to bid into our RFP process. It may be 6 months later they're ready to actually find an offtaker, and so we will still evaluate those. And again, kind of using the same apples to apples comparison of our incremental cost analysis. And then similarly, we do a lot of work trying to identify new RNG project development opportunities, and so. This might be, working directly with a landfill that is interested in doing RNG, but maybe they haven't found a developer that they want to work with, or maybe they're not interested in accessing that transportation fuel credit market. And so we will work with a potential, feedstock potential supplier. Will typically, enter into some short period of non-disclosure and non-binding, negotiation to sort of figure out, you know, hey, is there something here? Is there enough feedstock? Do we know what the technology might be? How does that interconnect option look? Is there a pipeline nearby? And so we'll evaluate that and try to get to the point where we can say, you know, yes, this deserves more attention, or no, it does not. Let me pause here. Tim says, you mentioned that you have contracts for 3%, but that some of that is options instead of actual purchases. Do you have a sense of what percent of the Northwest Natural Energy will be actually is here? Thank you, Tim. So yeah, a little more context on that 3% number. So right now, under contract for delivery, we expect to be at about 1.6% with current contracts at the end of this year. There's a couple other projects that we have the option to develop, and we're doing some more diligence on that. And then there's also, and then that's what kind of gets to the 3%. There's also a couple of other offtakes that actually came through our last RFP that we're still currently evaluating. It's likely that we will execute some contracts with some of those resources. Some of those are set to begin delivering in early 2023. And so it's kind of going to get us closer to about 5%, I think, by 2023. So there's a couple resources still in the works, but yeah, right now under contract is about 1.6%. I think Kara had another question too.
Yeah, thanks, Anna. So you mentioned a couple of things that you consider, and I'm guessing many of these are outlined in your RFP when they go out, what kinds of things you're looking at, criteria. Curious, though, whether specific environmental benefits to Oregonians are kind of higher on the list.
Yeah. I think, I'm not sure if I think you cut out a little bit, but you said
I did.
Environmental benefits to Oregonians. And
yeah.
Did you say something after that?
Oh, just one, just thinking about developing a project in Nebraska isn't, is great, but, not maybe for Oregonians in particular. So maybe talk a little bit about where, if at all, that criteria comes into play.
Sure. Yeah, thank you. It's a very good question. So a couple ways that I would answer that. So the first is that we are, primarily looking at RNG as a greenhouse gas benefit in terms of the environmental benefits. So to that extent, greenhouse gases being really a global pollutant, we do believe that reducing greenhouse gases anywhere is going to benefit Oregonians. Now, there is in our current way that we approach our cost effectiveness evaluation, and we think about the avoided costs of different resources that Ryan also will talk about. There's no in the Senate Bill 98 rules and in statute, there's no specific, I would say, way that we can weigh additional benefits to Oregon customers, because what we are looking at is really the cost effectiveness of a resource. However, that said, in our most recent RFP, and this will be in the same for this next RFP, we did want to acknowledge the fact that there are other benefits and other considerations for RNG resources that are a little bit different from kind of the things that the Senate Bill 98 rules might point us to. So we tried to add a whole part to our RFP that looked at, are there other types of environmental benefits here? And specifically, are there some benefits to, I think we put in our service territory. I'd have to go back and look. We also looked at, is the developer, using equitable hiring practices and things like that. So things that kind of were outside the box of how we had traditionally looked at resources, how we traditionally look at just a lot of our other gas resources, and that. So we tried to give a little bit of weighting to that. I would say it's not very heavy weighting towards, specific environmental benefits to Oregonians, but we are, primarily driven by that reduction in greenhouse gases, which then is retired on behalf of customers. So no one else is claiming that global pollutant reduction. So it's a little bit of a maybe not a complete answer because we're still kind of working on how to do that, but we're a little bit limited by the regulatory structure, I would say right now.
And if you don't mind me jumping in here too, Anna.
Yeah, sure.
There's one of the things that when you dig in a little bit more to the work that Peter and Morris were presenting, of course, like maybe wastewater treatment is associated with population, so cities and things, and similar to how a lot of the resources that serve Oregonians on the renewable electricity side for wind, for example, might be in windy places, Montana or Wyoming, and some of the solar resources might be in sunny places. Because of the waste streams that we're looking at here, the middle part of the country has a lot of the resources. So you kind of think about like a wind resource potential map. If you thought about like that for a waste stream map, you could just kind of think through maybe where a lot of those are. But I think it's similar to the approach that, in terms of IRP evaluation of resources, I think that we're taking an analogous approach to what's done on the electric side.
Thank you, Ryan. I know we've got a lot more to cover today. So I think we can go to the next slide. I'll talk a little bit more about kind of how we're, well, actually, sorry, maybe go back because there's one point that I did really want to make, which is very relevant to why we're here today. So the RFP process, the other evaluation, the rolling evaluation of these projects, we are most often having to make decisions about whether or not to move forward with a project or whether or not to enter into definitive legal agreements with project developers or producers of RNG. We have to do that typically in a time frame that just does not work well with an IRP. So you can't say to a producer, hey, yeah, this is a really good RNG deal. We think that this is a good resource for our customers. We'll put this in our IRP. We'll wait, many, many months, maybe a year for acknowledgement, and then we'll get back to you. And that's just not going to work with how this market operates today. So typically a developer is going to say, hey, I'll sign a 90-day exclusivity agreement with you. You have 90 days to do your diligence and figure out if this is a good resource. And then we need to enter into definitive agreements or I'm going to leave and go find someone else. So it's a much faster process. And so we have to be nimble and we have to be able to take advantage of opportunities as they are in front of us, which is why there are not necessarily specific resources in the IRP. It's more that we've got some different tranches that are representative of the types of resources that we see, but we can't really put specific resources in there because we just don't have time to sit and wait for that process to to finalize before we go back to a resource and sign definitive agreements. So I think that's something important to recognize of the way that the industry is working today. Okay, now you can go to the next slide. So our last RFP, we were really excited by how much just the level of responses that we got. So we got 27 individual resources. And again, proposers were welcome to propose whatever length of contract they desired. We didn't have a set volume. We were just kind of saying, give us your best deal and then we'll evaluate those. So the average term of the contract was about 14 years. Average annual volume, a little under 600,000 MMBTU a year. So that's, for context, it's a little bit under 1% of our organ sales volume. So some pretty big projects came in this last time. And then we also allowed people to propose both bundled and unbundled resources. And there was a pretty even split between the two. And you can see this pie chart is a breakdown of what the feedstocks were. So a very large chunk of landfill resources, that's the yellow one. And then actually quite a few manure-based projects, and then just a whole bunch of others that came through. And we were also pretty surprised by the diversity of the responses that came in. So we have 2 resources that we are actually still working through kind of some final negotiations with them. And I think that came out of this RFP. I think we will probably end up executing some agreements. Those 2 resources are primarily landfill. There's those tend to right now at least be the least cost resources. But then, as I said, in a couple of weeks, we're going to put out our next RFP. Should be really interesting to see what we get out of that. And so in the next slide, I'm just going to talk a little bit about kind of the I think to Kara's point, sort of the things that we look at when we're thinking about a resource. And this is an example of our summary diligence for an RNG resource. And so we have a whole internal group that focuses on really diligencing any of these options. And so, we might get a resource and it sounds great on paper, but then we dig into it and we find that actually, the funding that they've claimed for this resource is not present, or maybe the interconnection has actually not been undertaken, and maybe it's going to be pretty difficult to do, and we can't actually expect that gas is going to show up on the pipe. So just a lot of different streams of diligence. I'm not going to go through each of these, but really, if you look at kind of the teams on the left, that's really all of the different internal teams that we ask that they bring their expertise to bear on these resources and help us really evaluate these things. So it's a pretty long process, but it's we find lots of interesting things. we find reasons not to move forward with resources for sure. Okay, if you go to the next slide, wanted to dig into kind of what we're doing right now. So first, I want to talk about our offtake. So these are purchases of RNG and RTCs that are from projects that we have no involvement in other than just being that off-taker. So we have 3 contracts that we have signed. Those total agreements, there's some different ramps up in production, but in the first full year, 2022, we expect a little bit under 1 million decatherms, and so that's a little bit over 1%. And then I said to Tim, we have about 1.6%. So there is some additional resources from projects that are in development that get us to about 1.6%. 2 of these resources are currently in our PGA. The other one will likely, some of it may show up in our next PGA. There's some other, I talked about kind of all those different policy frameworks that are driving us to go procure RNG. Some of this 3rd contract, some of those RNG resources may end up for Washington customers and for potentially some of the other voluntary activity that we're doing. So one resource, we signed a 5-year deal. It's a organics waste processing facility in Utah. It's a pretty small contract, so it's about 200 decatherms a day. And this is a facility that processes mostly like leftover materials from commercial food processing and manufacturing. So like one of the things is Oatly, which makes oat-based milk. There are some I don't have the technical words, but there's some residuals at the end of that manufacturing process that all gets taken to this facility. So it's again kind of that manufacturing of food products type of scale that goes to this facility. The other facility that we've signed a contract for that's currently in our PGA is a wastewater treatment facility in New York. And this particular contract also includes a dairy-based digester in Wisconsin. And so the agreement that we signed has RTCs really coming from both places. This is a 2-year contract with an option to extend, and it's a little bit larger. It's about 1,000 decatherms a day, which over, if you annualize that, that's about 0.5% of our organ sales volume, something like that. And then the third contract is a really long contract that we signed. It was a 21-year contract, and this is a portfolio of landfill facilities that are producing RNG. And this is a contract that starts at 500,000 and then it ramps up to 1 million decatherms a year. So those are, I think those were all executed in this past 12-month period or so. And if you go to the next slide, I can talk a little about the project development that we're doing. So you all may have heard we signed an agreement with a developer and Tyson Fresh Meats. And so this is an option to develop up to 4 projects on Tyson Fresh Meats facilities. And so Tyson Fresh Meats is the arm of Tyson that does beef and pork processing. So we have 2 facilities in Nebraska. One of them is operational. We reached commercial operations a couple months ago, which is very exciting. And then another one is in early construction phases. And so both of the facilities are really large beef processing and packaging facilities. So the biogas is really a product of all of the water that is used in the facility, and it's used. There's slaughtering and there's beef processing and packaging. There's a lot of water that is involved in that, and that is really where kind of everything that was in the meat that doesn't end up in a consumer product, it is collected in the water, and then that is all taken to a lagoon. And so each one of these facilities has a lagoon like this. These are facilities processing really enormous amounts of meat. You can see one of these facilities is the largest, one of them is actually the largest beef processing facility in the US. The other one I think is in the top 10 or something like that. So these facilities are producing just immense amount of meat and then immense amounts of wastewater that's part of this process. So the project that Northwest Natural is engaged in is to really utilize that biogas that is coming off the lagoons. It's being captured under a kind of this, we call it a bladder. And then it's being cleaned and conditioned with a couple of different technologies. There's different technologies at each of the facilities. We're taking out the various impurities, and then we are compressing it and putting it into the local gas distribution system. So Mid-American is the gas distribution system for one of the projects, and Black Hills Energy is in the other. If you go to the next picture slide, I have a couple pictures of the first facility. So this is in Lexington, Nebraska. This facility, this is the one that is operational. It hit commercial operations in January. So on the left, this was very, very cold. On the left is the outside of the gas cleaning skids. So there's just this box that helps kind of keep keep the climate fairly warm inside. This is where all the different membranes sit, and the top right picture is a picture of the membranes that the gas goes through. And then that bottom middle box is just a picture of what the actual physical interconnection to the local Black Hills distribution system looks like. So all of the piping and the regulators and everything that make sure that the gas that's coming out of the project is at the right pressure, and all of the quality measurements are taken there, and that's where there's valves that can be shut off in case the quality is not good enough for the pipeline. I think there was a question. Someone had their hand raised.
Yeah, Anna, thank you very much. This is Tim Miller again. It strikes me as you're describing this that, and I wonder if this is a criteria that you consider in your contract reviews, some significantly different externalities from the different sources of RNG. Obviously, using a wastewater, a local wastewater treatment plant is very different from getting RNG off of a giant feedlot and slaughterhouse, somewhere in the Midwest, where whether you're looking at their labor practices or what the underlying product is or what's going on there. Are you able to consider those different externalities? Because that's a yeah, a lot of unpleasant byproducts coming out of this particular source. Yeah, I applaud the RNG acquisition. I'm just saying, can you consider those things, or does our Public Utility Commission not enable you to do that? And if so, how can you make them enable you to do that?
Yeah, all great questions. So, you know, when we're looking at sources like this, we are looking at existing sources of methane that are being vented to the atmosphere or flared. I mean, a project like this, you know, one thing that we have done is we looked at kind of all of the piping that was on site. We noticed that there was a bunch of oxygen intrusion. Turned out there were some leaks. So this project allowed us to kind of go in and replace certain parts of the piping that was already on site that collected the gas. And that kind of goes back to what I mentioned earlier, which is that RNG projects can drive, you have this economic drive to capture all of the available gas. So, you know, we're really looking at not, you know, uh, not trying to make sort of new sources of methane that didn't exist or new sources of, you know, pollution, but really taking advantage of stuff that's already there and then trying to do something more useful with it. And that often does have, you know, local benefits to air quality. But, you know, I think to just your broader question about externalities, you know, there's no real framework that allows us to put kind of a quantitative value to that. But I think, you know, again, we're trying to integrate more of that into our RFP. We're also trying to make sure that, you know, when we're working with partners, like when we're working with Tyson, we understand, you know, what are their sustainability goals? What are the ethics that drive that company? What are the, you know, do they have in place, you know, parameters around their workforce that align with Northwest Naturals? So there's a lot of kind of other types of, I would say, more qualitative assessments that we make that's part of our diligence. But really, there's no framework for that quantitative valuation of any other externalities. But I would say, again, that mostly RNG projects are going in and they're capturing stuff that's going to be, you know, vented or flared. And in many cases, you know, like with dairy projects, you can have a lot of positive externalities there. You know, you're improving the groundwater, things like that. So, you know, I think on balance, these tend to be quite beneficial to the local airstream, the local water quality, rather than, you know, more detrimental. I don't know if that answers your question. I mean, it's a good question. We don't really have a framework to do that.
Got it. Thank you.
Yeah. See a question from Laura here. How you evaluate RNG options? Does the MRET system include life cycle carbon intensity, and how is that factored into your selection? The social cost of carbon part of the cost effectiveness analysis? Yes. Great question. So yes, when Ryan gets into our cost effectiveness analysis, I think he'll talk a bit about how we apply the social cost of carbon to these projects. But then to your earlier question, so MRETS does require that you have a carbon intensity score associated with each resource, and that is kind of linked to every single RTC. And in our annual reporting, we will be reporting the carbon intensity of each resource. The way that we report our emissions in the various you know, state and federal paradigms where we report our emissions currently does not differentiate between resources with different CI scores. So we are reporting, you know, this amount of RNG or this amount of hydrogen or this amount of conventional gas, and there's no kind of additional benefit ascribed to RNG that has, say, like a very, very low and negative CI score. So consequently, at this point, when we do our cost effectiveness tests, there is no way for us to value very low CI score RNG, but we do report it, and we will report it, and it's a part of what we ask for every RNG project that we procure. Laura, I don't know if that answers your question, but I'm happy to dig into that a little bit. And okay, I see a couple other questions here. So related to that, are leaks included in this assessment? Leaks in like at the RNG site, or I don't know if Greer, if you maybe just give me a little more context of.
Yeah,
I might
so
hop in here too, and oh, sorry. Go ahead, Greer.
yeah, thanks. I guess I was just thinking at the site along the, distribution and theoretically, and I know there's different scopes of emissions that could be considered. So just wondering what you consider.
So for the CI scores that are affiliated with each resource, there's kind of a circle drawn around the individual resource that is including kind of everything that's on site there. So it's going to reflect everything up until the point that it enters the local distribution system pipeline. Ryan, I don't know if you have more to add there.
Yeah, on the side when we're comparing it in terms of incremental cost to the geologic gas alternative, we compare based upon the kind of regulation in the state. So for example, in Washington state, there's a policy that says we include the not only deploy the social cost of carbon, but also include the upstream emissions associated with conventional gas delivery and production in that assessment. In Oregon, the primary policy that will between SB 98 and the Climate Protection Program, there's no direction on that. And specific to the Climate Protection Program, upstream emissions are considered like out of boundary for the program. So there's the upstream costs are not included in the avoided costs like they are in like a Washington state specific evaluation. But we will talk about avoided costs in a fair bit more detail. I'll breeze through them a little bit today, but we'll go into the avoided costs in a lot of detail at the next working group. So it's kind of on the carbon intensity side, it's included in the MRES stuff, but also on the avoided cost side too, relative to comparing the renewable sources with the conventional geologic sources.
Thank you, Ryan. Okay, just a couple more slides to help kind of finalize painting this picture of what we are procuring right now. If you go to the next one, Ryan. This is just, I kind of talked about the resources that we have under contract. So we have 3 offtakes and then 2 of the projects that are development projects, and the weighted incremental cost of these for the period of time under which they are contracted is $7.38 an MMBTU. So that means above the cost of conventional gas. Now, again, Ryan will talk a bit about kind of everything that goes into that, but the overall variability in price, I'm going to show you on the next slide kind of what that looks like. But in terms of how we think about what types of inputs are going to be in this IRP, we're looking at the resources that we have in front of us. We're looking at resources like those identified in the ICF study, and then also just what's coming through our continual RFP process. So you go to the next slide. So this is a slide that reflects the portfolio of resources that we are evaluating for development, as well as our 2020 and our 2021 RFP. And so what I have here, just the blue bars are pure offtakes, the green bars are development opportunities. And so, all told, everything that is in front of us here, I mean, you can see there's a really big distribution in the overall bundled price. This represents, though, over 35 million MMBTUs a year. So that's about half of Northwest Natural's annual Oregon sales. Now, we're not going to go after all these RNG resources. We don't need all these RNG resources right now. These are resources, though, that are in front of us. And so when we're looking at these, we'll do our cost effectiveness test and we'll look at that. But then, like I mentioned, there's all this other diligence that we do. So the development projects tend to be a little bit cheaper than offtake opportunities right now. The main driver of that is really the type of capital that is behind these projects. So, when a utility is looking at developing a project, we have our set return on equity, and that's really the return that's built in. The projects that you're seeing developed primarily in the RNG space, there's a lot of private equity that has really driven that substantial growth in RNG projects. That private equity, they're looking for returns of quite a bit higher. So we're really competing in some cases with some of those really lucrative transportation fuel credit markets in some cases. And with those returns that the private equity dollars are looking for, there's an openness to maybe more risk on the revenue side. And so again, as I mentioned, the utilities and commercial customers that are buying RNG, they can really be that long-term steady revenue. And that might be a good fit for certain types of money in the RNG space. So we look at these resources and we try to come up with kind of the different tranches. And Ryan will tell you in a second what we're planning to use for this IRP, with the caveat that we are running this RFP in a couple of weeks here. And so if there's new information that comes out of that RFP that really says to us, hey, we really should have a tranche that's much lower, or maybe the second tranche needs to be a lot higher, we will reflect that. But I think a really critical thing to think about in the RNG resource arena is that it's not a liquid market. And so it's not as if everything is available at these different prices at exactly the same time. So things kind of come and go. It's a little bit chunky in how you have to procure and build a portfolio. And so that's kind of why looking at this from a couple of different tranches makes a lot of sense to us. Let me just make sure I have a couple questions here. Curious why Element Markets is producing much more RNG this year than it is expected to next year. So that is just really a function of the timing of the contract. So we signed a contract for 2 years with an option to extend for the third. And so the contract started in kind of I think it was like third quarter of 2021. So it's at the 2 years, it'll wrap up, at some point in 2023. So the volume we expect from Element is anticipated to go down a lot. We could renew it, and we could certainly sign a contract with a similar volume, but that's just a reflection of what we've contracted for right now. And then could you translate these prices into price of a ton of GHGs avoided? Gosh, I don't have that number on hand. Looking to the IRP team.
Yeah, so that's a lot of what actually the incremental cost calculation is about. It's a great question, Tim. It's all a little bit of maybe a plug to. That's what we're going to get into here in a second. It depends upon each of these projects. I'll turn my camera back on. Sorry. Each of these projects will also have its own avoided cost. So there's different attributes associated with each one of these. Like if it's something that could be delivered to us, and there's different costs that can be avoided with the different projects. So it's not as simple as just subtracting one number from all of them. And also it depends on the timeline, how long they would be expected to go. Of course, we expect the price of conventional gas to go up. So it's not that simple, but in a just really kind of back of the envelope, like at $10, is an incremental cost of roughly $6, which is about $100 a ton-ish, kind of in that range. But there's some costs, there are some projects that will have higher avoided costs for different reasons, which means that the incremental cost and therefore cost per ton of GHG reduced is lower. I wish it was as simple as saying just divide it, but it's not that simple. So.
Thank you. I think that's actually all I was going to say on this slide, and then I was going to turn it to you, Ryan, just to talk about the inputs to the IRP. But yeah, always happy to take more questions on RNG if anyone wants to seek me out later. Thank you.
Thank you so much, Anna. And yeah, so we'll get going quickly. Chris is a great presenter, really interesting stuff in hydrogen, so I'll try to get through this. So this is that same supply curve that was presented for the 2019 study that that Morris and Peter were presenting from ICF. And what we're trying to define, what we see is this kind of aligns with the supply curve that we have right now for our resources. And again, they said, there's a supply curve that's fixed in time. It could be the cost could be going down through time or something, but we want to take an approach that is that incorporates our well, our hard-earned market intel in this space, and also the newest work that we see from parties relative to the national resource that we're looking to tap. And I think that what we've come up with here is combining all those things and working with Anna's team to come up with a fairly conservative approach relative to our base case assumption. We'll talk about the uncertainty here in a minute because that's important. But as Anna was showing, think about like if you were like a real estate developer or something, you decide that you want to get into some neighborhood that's already existing. You can only buy houses that are for sale. So there might be some ones that you really want the most, but the ones that you can get your hands on at any given time are the ones that are for sale. And with that, so we'll see and even the resources that we have committed to have different costs, different incremental costs. So we're representing that in the IRP process in terms of the modeling with here's a rough portfolio cost of how much this smattering of resources that we expect to get in for some volume that's tied to this ICF cost curve here, and we'll deploy that for different volumes. So for example, there's this first part of the supply curve here. It has roughly this area that has roughly a third or so of the RNG available here. And what we take is, okay, well, we're saying we'll take 1350 as an assumption of what the smattering of resources in the near term might cost in terms of bundled MMBTU. And then we know that there's uncertainty around that. So we're deploying a plus or minus basically of about $3 in MMBTU for a portfolio cost for a tranche approach or a portfolio cost of resources in the nearer term. Of course, if you're going up the supply curve, this would be kind of maybe what we might expect the resources on a portfolio cost might look like. And then as we move up later on in time, you get some of those more expensive resources. If you remember back to the presentation from ICF, like these might be associated with certain types of feedstocks like landfills and wastewater treatment plants and animal waste, where this could be biomass gasification, some of potentially food crops. Longer term, of course, so we want to generally get this stuff first, and then that's around $19 and a little bit more uncertain, so plus or minus in terms of a 10% 90 percentile, kind of building a distribution for a risk analysis that has kind of confidence intervals of 10 to 90%. So roughly 80% would be expected to fall in this range in terms of the portfolio cost. So that's kind of how we're planning to put those pieces together, because as Anna discussed, we won't we would really make it harder for us to get a lower cost portfolio of RNG for our customers if we were evaluating specific resources in the IRP and trying to fit that square peg into that round hole. Think of it like if in the current housing market, if someone was to make an offer for a home and say, well, we want to maybe look at all these other houses and we'll get to you later on, and if you're but a lot of times those houses would, of course, in the hot market like now, might be sold. So there's two kind of approaches: what we're using to input into the model, which is what we're showing here, and the second piece is the renewable gas evaluation methodology, and that's what we use to evaluate specific resources between IRPs at any given time. So when we get the RFP results back from the RFP that we'll have out, we'll use this methodology to evaluate those projects and start potential negotiations with counterparties, knowing that it's not going to align with the timing of the IRP. We kind of saw this coming in the last IRP and proposed a renewable resource evaluation methodology initially in the IRP. It got taken up on at least in Oregon in a separate process, and resulted in a approved methodology for evaluating renewable resources that happened in UM 2030 in Oregon. And then also the SB 98 rules, I can't remember exactly the number of the rules there, but the SB 98 rules also have a provision that says this evaluation methodology will be looked at anew in each IRP. So that's what we're going to do here. So we spent a lot of time in the last IRP process going through the big picture things of this methodology. It's very involved, and we want to make sure that it's transparent to folks. So after thinking about it, we're almost at 4 o'clock now, we're going to have a supplemental technical working group specific to this methodology. It'll be after the next technical working group, at least, because the next technical working group we also talk about in more detail our methodology for avoided cost, which is an important part of evaluating RNG for that incremental cost. But we'll go through it at a really high level now about what it's doing, and then know that we'll have an opportunity to dig in and take a look at the workbook that we use and apply to each one of the resources. I think it's fair to say we can point folks to resources that we put out in the previous IRP and in the 2030 process. At a high level, those things still all hold. There have been some small changes just to be able to implement moving from, in the 2018 IRP, a looking forward process, working closely with Anna's team to be able to apply that methodology to make sure that we're comparing resources apples to apples in a way that can work for the resource for the business development team to get these great resources for customers. So there's some small modifications to the methodology that was presented previously, more just about how to, as we've had more practice in this market, and kind of think things through. So that's just a teaser. We'll go into this in a lot of detail at a supplemental technical working group, but at a high level, just thinking about renewable natural gas versus conventional gas, we want to be able to compare these in what we call the all-in cost. So the all-in cost of either renewable natural gas or conventional natural gas is the cost of the gas, the cost of any greenhouse gas compliance costs associated with combustion of that gas. So right now, the way that the RNG markets work, that would be zero for RNG resources, and it would be a social cost of carbon or higher for the conventional case. And then if it is a system, if it's an on-system resource, then we would also include the avoided capacity cost or infrastructure costs associated with being able to get that on-system supply, and kind of offset some of the costs associated with the resources that we discussed in the morning. For example, additional storage resources or additional pipeline resources to be able to get gas onto our system. Of course, those resources that deliver gas right onto our system provide that benefit. So if you calculate the all-in cost of conventional natural gas, the all-in cost of renewable natural gas, and look at the difference, then you have your incremental cost, and that's kind of what we want to look at to be able to compare resources to what is the lowest cost in terms of incremental cost, knowing that having all those market complications that Anna discussed. And then I'll move on to the next one. At a high level, another thing that's really important to keep in mind is that we do a risk-adjusted decision-making process for all of our IRP resources. So in one of Anna's slides, she had a number that said a risk-adjusted incremental cost. And that risk-adjusted means it has a penalty. All of these things will have a penalty. So it's kind of like, okay, well, what if there was a bad outcome here? For example, on the conventional natural gas side, it could be, prices spike. For whatever reason, right now there's unfortunately like a war going on that's impacting those global markets. Whatever it is, there could be reasons that gas prices go higher. So that would make, of course, in terms of incremental cost, the cost of RNG relatively cheaper. One of the bigger drivers is what is the greenhouse gas costs that are implemented. So one of the trickiest things, as we talked about at the very first technical working group and at a supplemental working group last year, is how to implement this. We've used carbon pricing as a methodology in previous IRPs. That's complicated this time, given that the policies that we have in our states have emissions caps for each year. Now there are some compliance tools that make it so that you can use a price in some instances and some not in others, but you can model, okay, well, emissions can't be above this, right? And then also select all the resources, kind of moving up the cost curve to be able to meet that. So it's a little bit tricky now that we are doing a full IRP, but we use that IRP process to inform the risk also on the greenhouse gas compliance side that would be fed into the workbook that is used to basically act like an IRP process for that specific resource. So we can do that for each one of the RNG resources that we're evaluating to see which ones look like good ones compared to the rest of them. So here is a really quick example. This is a simple one. The costs are bucketed at a very high level. A lot of these projects are especially development projects, are far a bit more complex with a lot of different components that add up to this here. But in this case, we're just using a simple example of an on-system resource where there's an RNG resource that is contracted for a bundled RNG resource that's contracted at some dollar amount in current dollars, and then due to inflation, that goes down in real terms through time, and that's compared to a conventional gas resource. And this is, say, I don't know, 20 years as an example. And the costs avoided from the conventional gas alternative are the gas costs here. The infrastructure costs, because it's an on-system resource, are represented by the yellow one here, and then the greenhouse gas compliance costs or the carbon costs are represented in orange here. So this kind of shows what we see in a lot of these resources and why a lot of times a longer term resource is more attractive for our customers. That the incremental cost in a given year is represented by the difference between the RNG cost and the conventional cost. So the incremental cost is positive, and then eventually it switches and goes negative. And then what we're evaluating resources on is taking a look at the levelized value of that difference between the price of the cost of the RNG and the cost of the conventional gas alternative. So what's also important to keep in mind here, though, is that all of these components are uncertain. And we want to make sure that we account for uncertainty and don't kind of make risky decisions where you turn out to regret them. Make sure that we're evaluating that. So we won't get into this in a lot of detail today. Pass over to Chris, but this just shows the distribution of the different components for one of the projects that we were looking at. Where incremental cost, of course, is the cost of the RNG minus the avoided cost of conventional gas, and then you see there's a base case, but then there's a distribution around it where the incremental cost has this kind of distribution where you can see the wider that this is like this is half of the values are in the box, 95% of the values are within the whiskers, so it kind of shows you the bigger these are, the bigger source of uncertainty is. So the biggest source of uncertainty is still kind of the the price of conventional gas and the greenhouse gas compliance costs. There is, of course, risk, and this is something that's evaluated very carefully by the renewables team, including like the output of the project, and those different cost streams that make up an RNG project. So all these things, you add up all these, subtract all of these out, and get the incremental cost, and is quite uncertain. And we use a risk-adjusted metric, which penalizes all of it for being risky. So the riskier projects, in that sense, have a bigger risk adjustment, a bigger a risk factor that makes the risk-adjusted incremental cost look closer. So, maybe in the expectation, for example, if there are two resources, one has an incremental cost of 10 and one has an incremental cost of 5. If the one that has an incremental cost of 5 has a much greater potential to potentially go way higher than 5, to say to 20, there's a 10% chance it goes to 20, but the one that's $10 incremental cost has a 0% chance of going to 20. Then you evaluate those things, and kind of bring those costs together using that risk-adjusted metric. But again, we will have a few hours to discuss this topic because it's an important one, and it's one that we talk about the methodology, but not actual resources in the IRP, just because of the market components. I'll leave you with this. It tells you something that we looked at with in the process between IRPs, and tells you how often we update the things that are used to evaluate the incremental cost of the resources that we're looking at for renewable resources. We have that in the renewable natural gas or biofuels section right now, but we use the same methodology, of course, to look at all renewable resources like hydrogen, but it's just in the near term. We are, of course, looking at hydrogen resources, but just kind of like all that you've heard today, maybe in the near term, not just RNG, but specific types of RNG are the types of resources that we're most likely to be going after, and as teams looking at more closely. With that, I'll take any questions and hand it over to Chris. And sorry, Chris, you're a bit pinched, but we'd love to hear some more about hydrogen.
Great. Final stretch here. Half an hour. Hydrogen, carbon capture, and a potential pilot that we'd like to talk about today. So let's dig into it. So hydrogen, next slide, please. So briefly, Chris Craker, I'm in our renewables group here. I work under Anna to source out new sources of low carbon, low cost gases, and hydrogen is what the area that I focus in on. And why do we focus on hydrogen? Well, it's molecules. We need those molecules to deliver that energy to customers. And if you combine the molecules from hydrogen to RNG, we really have no constraints on having enough molecules to continue to do that. So we deliver a gaseous energy product to our customers today. Hydrogen is a gas, so it fits great into our current operations, our distribution system, for our storage system, as well as downstream appliances. So it is a really great fit. There's a lot of diverse supply for hydrogen, which we'll get into in a bit. It truly is a low-cost resource. As we, look at things temporally right now, it's a little bit different than in the future, and we'll go into those cost curves in a little bit. We have some industry here that needs high temperature energy to do the work that they do. Hydrogen can continue to enable them to do that. And then the nice thing about hydrogen is that allows us to enter into new markets such as trucking, aviation and marine fuels, and also to help decarbonize the electric grid a little bit quicker and a little bit more cost effectively by providing long-term energy storage to the grid, which we touched on a little bit earlier today. Next slide. So real quick, I'm sure you're all very familiar with electrolytic hydrogen. That's basically using electricity to make hydrogen out of water. You pass electric current through it, and you have that water molecule that separates into hydrogen and oxygen. We take the hydrogen and do something with it. And the oxygen, typically, we just vent it, as it really doesn't have a whole lot of value right now. This process is very energy intensive, and it is as expensive as the cost of electricity is. So the cheaper the electricity is, the cheaper that hydrogen comes from this process. And right now, electrolyzers that are used to make hydrogen this way are quite expensive. And so having distributed generation coming from electrolyzers today doesn't make a whole lot of economic sense. The utilization factor for those is going to be very small, and so the cost of that gas is going to be prohibitive. But over time, those costs are going to come down, and we're going to start seeing a better economic case for distributed hydrogen generation. However, large-scale electrolyzer plants, because of their high utilization factor, could become more cost-effective quicker. And then the other way we make hydrogen typically is by reforming natural gas. And we can do this in a few different ways. But the idea is that we take that CH4 molecule and we split it up, chop it up, and we take the hydrogen and we put that into the pipe or do something with it. And then we can take the CO2 and sequester that into the Earth's crust, into an area where it will never come back out. And that's typically using a process called steam methane reformation. Actually, SMR or steam methane reforming isn't really being proposed for reforming natural gas too much in the future, just because it's not as efficient from a carbon sequestration perspective. There's newer technologies called autothermal reforming and partial oxidation that are much better for that kind of thing. The other way that we can make hydrogen out of natural gas, which is kind of cutting edge, it's called methane pyrolysis, and that's where we take the CH4 molecule and chop it up, again, taking hydrogen off of it, but the byproduct is just pure carbon. There is no carbon dioxide associated with it. It's just a powdery carbon form that we can dispose of either in a landfill, or we can have secondary market use for it, such as use it in tires and things like that. And there's a few different ways to do that. That process can be done with electricity, or it can be done with just heat, or it can be done with using a catalyst. So a few different ways, and there's a number of different parties working on that. And we're going to talk about that a little bit more coming up. Next slide. We talked a lot about methanation today. I'm sure some of you have some questions as to what the heck that actually is. So basically, it's just taking hydrogen and combining that with CO2, carbon dioxide, to make CH4. And the nice thing about that is you don't have any blending issues. Right now, we feel we can blend about 20% hydrogen into our existing natural gas system. But with synthetic methane or methanated hydrogen, there are no blending limits. So you can make a massive amount of hydrogen and combine that with carbon dioxide and use your existing distribution system. And if you tie that in with an RNG product or process, RNG creates methane from biogas, which is a mixture of carbon dioxide and methane, and typically vents that CO2. So if we grab that CO2, combine it with hydrogen right at that RNG site, we can leverage the compression that we already have in place. We can leverage the interconnect we have in place. And so the capital costs of that actually go down per unit of energy that we're producing. So that could be a very nice solution to essentially double the output of renewable gases going forward. When we talk about methanation, there's two ways to do it. Well, there's probably more than that, but the two main ways are the biological method, and then there's a chemical method. The chemical methanation method has been around for over 100 years. It's robust, and it's a steady state process that uses a catalyst to methanate the hydrogen with. It likes steady state operation, and so it doesn't like a whole lot of variability, but it does create some useful waste heat. So if you have an industrial source nearby that needs waste heat, you can actually use that nearby. The biological methanation method is fascinating to me. Basically, it's being done by a bug, for lack of a better word, called an archaea, that eats carbon dioxide and hydrogen, and its waste product is CH4 and water. This is a very flexible operation. It can stop and start, ramp up and ramp down at a moment's notice, and is very robust from contaminants that might come into it. So if you couple this with gas from a landfill, it's really, really great. So we've been kind of looking at both of these options, and they may become more and more important from a resource perspective in the future. We'll go to the next slide. Quick comparison of the carbon intensities of methanated hydrogen and straight hydrogen, electrolytic hydrogen, all of the hydrogen that we've been talking about so far. You can kind of see how they stack up. So comparing it to the Oregon 2019 grid mix, in grams per of CO2 per megajoule is the unit of measure there. The grid's about 100 grams per megajoule. That carbon intensity is going to go down over time as we get more and more renewables there. But as a point in time, this is kind of how things are stacking up. Our existing gas system has about 56 grams per megajoule of emissions. So that's the regular fossil gas that we get strategically sourced today. And then if you compare electrolytic hydrogen, which is using EWEB electricity, that's about 8 grams per megajoule. If we'd methanate that, we'd lose about 15% of the energy, making it about 10 grams per megajoule. And then you can look at the reforming processes that are extremely low as well. ATR, which is the autothermal reforming, the partial oxidation, or the methane pyrolysis hydrogen. So all of the hydrogen sources that we're looking at in the future are low carbon sources. I'll answer some questions. Has there been an achievable technical potential assessment of biogenic sources of CO2 for methanation? Yes, the ICF study took that into account, and their carbon source was just actually from biomass pyrolysis, not to be confused with methane pyrolysis. So basically, gasification of woody biomass creates carbon, and that's the carbon potential that they used in their study, which was very conservative, actually. They didn't really factor in any carbon produced from RNG sites. Will you also be looking at the future grid mix under HP 2021? Yeah, we can definitely update this slide and kind of do a directional look. This was just a snapshot in time just to do a quick comparison. Yeah. We'll go to the next slide. So the next question around hydrogen is always cost. How expensive is hydrogen today? And is this truly going to be a low cost resource in the future? And so the way we kind of look at this is through the lens of electrolytic hydrogen and through reformed methane hydrogen, either that blue method or the turquoise method, which is methane pyrolysis, which we'll get into in a second. So right now today, hydrogen sourced from the electrolytic hydrogen is really expensive. You can see on the left-hand vertical axis, that's the cost of hydrogen per kilogram. If you want to convert that to MMBTU, multiplied by about 7. So we're looking at around $28 to $35, maybe $40 per MMBTU. Very, very expensive gas. But as you can see over time, as the cost of electricity decreases, which it's predicted to do under increasing amount of renewables and overbuilding of solar and wind generation, that's predicted to decrease the cost of hydrogen substantially in the future. And you can see the cost of blue hydrogen, which is the blue. They kind of have parity around the 2030 mark there. And the cost of gray hydrogen, which is basically hydrogen produced from natural gas today, where the CO2 is just vented, which is not what we're talking about as a resource for ourselves in the future. But as for comparison's sake, that cost is down there in the gray. So again, the green is highly dependent on the cost of electricity, and you can kind of see how a production tax credit could work favorably to decrease these costs even more. So in the Build Back Better bill, there is a hydrogen production tax credit being considered. The BBB might be dead, but they are looking at a potential subsequent bill that would include some of these other tax credits. So a $3 per kilogram tax credit could reduce these costs significantly, and especially even the blue hydrogen sources, if they can meet the emissions requirements that the production tax credit is going to have, could be very, very low cost. Next slide. So when we talk about hydrogen, we kind of look at it two ways, not only in how it's generated, but also where it's generated. And just as Anna explained, we're looking at RNG projects all over North America. We're looking for hydrogen projects all over North America. And because hydrogen projects, electrolytic hydrogen really depends on the cost of electricity, we've been looking at areas where the cost of electricity is very, very low. So areas like Texas and Kansas and places like that where renewable penetrations are very, very high. And so these projects at scale are almost in the cost that RNG is today. And we're almost there, and not quite yet low enough for us to pull the trigger and go into one of these agreements, but very, very close. And a production tax credit could kind of push it over the edge. There are some barriers with these large projects that we didn't anticipate, quite frankly, a year or two ago. First one being, where do you put those hydrogen molecules? Right now, we can't just put a ton of hydrogen molecules into transmission lines or into other LDCs distribution lines. So that is limited until we're all growing and getting maturing as an industry to be able to having the ability to blend in the hydrogen, right? The other thing is we are actually competing for CO2 in some areas because of the sequestration tax credits that exist for carbon dioxide. So that actually makes the methanation process a little bit more expensive just because of that competition that's out there. So we are looking forward to a PTC, or production tax credit on hydrogen, to help reduce these costs. I'll go to the next slide. So that's kind of a brief explanation on the off-system research that we're doing. On the on-system side, we are looking at electrolytic on-system resources and reformed methane on-system resources. So the most near-term electrolytic hydrogen project we're looking at today is a project in Eugene where we're looking at blending in hydrogen from a 1 megawatt electrolyzer. We're currently working on a filing for that. And what this does is it allows us to learn how to do this safely and efficiently, and so we can start scaling things up for larger projects that are coming onto our system. And also it allows us to be able to receive hydrogen throughout our system. So third parties who want to come and inject hydrogen could conceivably be able to do that because we're ready for that. So we do have developers that have approached us to start some of these projects, which could be quite interesting. Next slide. So the other on-system resource we are looking at is reforming natural gas into hydrogen. And so two different methods here. So I've been talking about reforming natural gas with carbon capture. That's typically called blue hydrogen. We've applied that color to that production pathway. And if done right, can provide a really efficient and low-cost way to decarbonize, especially some of our largest industrial customers. Let's say we go to a pulp and paper plant and we provide them 100% hydrogen. That could be a very, very large decarbonization method for our region. So we're looking at where it makes sense in our region to do this. And for blue hydrogen, you need a place to put the CO2. And using the best DOE data we have available, as well as the data that we have from some of our MIST work, our underground gas storage, we've been looking for a good spot to do this. And there are possibly some low-hanging fruit near MIST, and we're continuing to explore that. And we'll get into why the MIST area in a few slides as we talk about hydrogen hubs. This is probably a little bit more long-term, but we're preparing for this now, actually. And the other thing I want to talk about is a methane pyrolysis on-system resource. So that methane pyrolysis process is often referred to as turquoise hydrogen. And I do apologize for the color attributes here. I didn't make them up. It's just kind of where we're at. So blue hydrogen is sequestering the CO2 in the Earth's crust. Turquoise hydrogen is taking that solid carbon and disposing of it in a landfill or something like that. And that's we have an immediate opportunity where we'd like to do a pilot to prove out the technology and see if it warrants more investment and and thought into using that as a near-term resource. Question here, is there more information about the blending project in Eugene? Not a whole lot more. So that project is shaping up to be about a 1 megawatt electrolyzer in partnership with eWeb potentially on eWeb property. And the idea would be to use eWeb power and water and to make hydrogen and inject that into a section of our grid, gas grid there in Eugene. So we are currently working on that filing. So we'll go to the next slide. So speaking of turquoise hydrogen and why we're proposing this project, if you look at the cost of production of turquoise hydrogen compared to pretty much anything else out there, it is quite stark as to how low it is. Very, very low production cost associated with it because you don't have to drill carbon sequestration wells. You don't have to have exploration activities to go find them. You don't have to transport carbon dioxide. You don't have to do a lot of different things. So very, very low cost potential there and very, very large potential because we can use the existing gas network that we have today to produce hydrogen wherever we want, whenever we want, at the percentage of volume that we want. So let's say we have a large industrial customer that could receive 100% hydrogen. We could generate that right on site and give them that 100% hydrogen. We could have a portion of our distribution system that where we'd want to blend in 10% hydrogen. We could do that with distributed turquoise generation. So this presents a really interesting opportunity for low cost, low carbon supplies on our system. So if you go to the next slide, we are proposing a turquoise hydrogen pilot for consideration in the upcoming IRP. So we're not the only ones considering this. There's Fortis BC, who's working with a company called Hazer up in British Columbia. They are working on a pyrolysis project. ATCO in Alberta is working with the University of British Columbia on a similar pyrolysis project. And there's also the Monolith turquoise hydrogen project that is being scaled up as we speak. So they recently received a $1 billion DOE loan to go scale up the existing facilities that they have today. So this is a lot of buzz and a lot of excitement going on in this area and a lot of research being done. And LDCs, or local gas distribution companies like Northwest Natural, are critical for this development because we can provide that feedback as to how these operate in the field and how useful they are, and any learnings, any feedback is appreciated to get the technology ramped up even quicker. If you look at the diagram on the right side, you can kind of see how the process works. You take CH4, which is methane, it comes into the process and it's heated up. And actually, some methods use heat, some methods use electricity, some methods use a catalyst, but something happens in that blue square, and the hydrogen pilot we're looking for is going to be using just heat. And what comes out of that is a hydrogen stream that would be delivered to the natural gas distribution system. And then a slipstream of that hydrogen goes up, over, and then back down into the heat process to provide that heat to keep the process going. And the only things that come out of this process are water, nitrogen that was introduced because of the air, and black carbon, so a solid carbon dust or powder that could be disposed of, like I said, in landfills, or we could find secondary markets for, such as using in tires to reduce costs even more. So the pilot we're looking at would be about $500,000. That is probably a little bit conservative, but that gets us a prototype that we can use for about 3 years to really shake it out and see how it works and see if it delivers on its promises. And the estimated cost of energy from that process is between $1 and $1.50 per kilogram, which is $7 to $11 per MMBTU. It is relatively new technology, so not quite lab scale, but a little bit further on. It's about a technology readiness level about 6 or 7, and we're going to help increase that level a little bit higher than that. The first project is going to be about 5 kilograms of production a day, very, very small, but us doing the project enables us to get first in line for subsequently larger scaled up versions, which will be 50 kilograms per day or even larger. If you go to the next slide. So the project is with a company called Modern Electron, and the idea is to have a prototype unit for on-system gas blending. We've identified a number of different industrial customers which would be suitable for receiving the gas, and we'd have that running for about 3 years. And the questions we're really wanting to answer is, how reliable is this technology? Will it fit with existing gas operations? Where do we put the black carbon? Is there any issues with disposal? Does it deliver on the gas quality? Does it truly just hydrogen coming out the other end, or is there anything else to consider? How close to zero are the carbon emissions, and can it deliver on that cost potential? And the reason why we need to answer these questions is because this is such a low cost resource that we could potentially get for our customers. Should we be putting more time and effort into this to ramp this up as quickly as possible, to decarbonize as quickly as possible using the lowest possible cost gas? So that's kind of the goal of that. And the learnings from the Eugene project will definitely help us expedite our work there. You know, what are best practices around any leak detection equipment or any field operations that we do. We're planning on learning how to do all that with the Eugene project, and that'll directly influence what we're doing here. So that prototype, we're looking around Q4 of 2022 and are targeting for an installation of early 2023 if everything goes well. All right, next slide. We've got about 6 minutes here, so I'll quickly go over hydrogen hubs. So very early on in the morning, someone was asking what our participation was in that, what we were thinking of that. So just some brief background here. The federal government has about $8 billion available for a minimum of 4 hydrogen hubs to be developed. That came out of their last year's infrastructure bill. Is there an opportunity for one here in the Pacific Northwest? There could be. We think we have a strong case for one here, specifically in the northwest part of our state. We have our mist storage assets there. We have a lot of electricity generation up there. We have a lot of industrial loads from pulp and paper, fertilizer plants. And so we do feel that there's a strong case to be made for a hub there. And we are actively talking to partners to see whether they'd want to come in as off-takers of that hydrogen and maybe doing some other things around exploration for sequestration, should that be a blue hydrogen project. So yes, we think there's something there. And so that would be phase 1, is kind of developing out that Pacific Northwest, the northwest portion of our state. But you can see how that might tie in to other areas of our state as the offshore wind project, if it picks up steam and we really start making hydrogen there, we could conceivably bring in hydrogen onto a repurposed gas line or a twinned gas line into our mist storage system. We could look at blending that into our Portland distribution system or anywhere along our distribution system, and deliver it to existing customers that use hydrogen today, such as the microchip manufacturing industry. So lots of potential around hubs. Next slide. The other resource that we're looking at is carbon capture. The reason why it couples with hydrogen is basically because of that reforming process where carbon dioxide is produced in the blue hydrogen method. So we are looking at that as a possible way to decarbonize our region's energy. And 2 kind of views of that. One, you can do it on the pre-combustion side. The other way, you can do it on the post-combustion side. There's pluses and minuses with both, but ideally it's lower cost to do it on the pre-combustion side by making hydrogen upfront. The other way you can do it is taking carbon right out of the air. That is very expensive right now, but could be a possible way of decarbonizing and also contributing to carbon supplies that we might need for the methanation process. And right now, the costs of this are very wide. It's some carbon capture is less than $20 per ton. Some of it is well over $120 per ton, depending on where you do it. Is it pre or post combustion, and exactly which process are you doing, and at what scale are you doing it? Are you doing it at the appliance level, or are you doing it at the power plant level? So a wide variety here, and we're looking to see where we can best use our resources to enter into some of these markets. Next slide. And really briefly on renewable energy storage, it presents an interesting opportunity for us to help decarbonize and the electric grid a little bit quicker and a little bit more cost effectively. Just because as we get more and more solar and wind, those variable resources, we're going to need to back that up with firm generation, which typically has been served by natural gas. In the future, that could be served by hydrogen that's been stored over time. So right now, our energy storage, we've got lots of it. We have about 6 million megawatt hours of storage available to us today. If that were a battery, that'd be about $2 trillion battery. It is truly a giant storage resource that we have available here today. And if we look at how the costs of that compare to some of other energy storage systems, such as lithium ion or pumped hydro, it is very, very low cost for this long-term energy storage. So the reason is because we're building that access to it. We're not actually building the storage. We have the storage. It's built. We need to build electrolyzers to help convert that renewable energy into a gas to get into the grid. So that could help with firming up electric supplies in the future. And if we go to my final slide, you'll kind of see some work that Caltech did to show how long duration storage, or LDS, could help reduce the cost of overall solar and wind buildouts over time, just because you don't have to overbuild as much if you have that storage available. So combining that long-term storage with solar and wind ultimately gets you the lowest cost. And I think we'll leave it there. Sorry if I went a little quickly over everything, but I want to make sure that we ended on time. So I'll pass it back to Ryan or the IRP team. And
thank you, Chris. That was impressive work, right on time. So we'll see if we might hang out. There's questions, but we want to make sure that we don't go too much over this. So the last slide really is just a summary slide of what we're actually going to be putting into our model. So similar to what we talked about with RNG, synthesizing the information on the hydrogen side. This includes both the biofuels and the hydrogen, both for blending or dedicated hubs or for specific customers, and then the synthetic methane, syngas, methane, hydrogen, however you want to think about that. And we have our base case costs here in the 10 to 90th percentile, and also with volume. So as we talked about with biofuels, we're using a constant cost curve through time. What's important here for hydrogen is that all of the projections for most of the low or no carbon hydrogen resources and synthetic methane are expected to go down through time because of the way the technologies work. So starting at $23 for hydrogen in 2022, and then moving down to $6 a decatherm in 2050. Similarly for synthetic methane or methylated hydrogen, starting at $32 now and moving down to $9 through time, and some pretty wide bands around that. And then we have the volume limits there. With that, we will hang around for a few minutes for any questions, but want to make sure we get you out the door. Like we said, we really love your feedback for this specific working group. I think maybe mid-April would be great if we could get feedback from you on questions relative to supply side resources. And again, the next one will be about demand side resources, and we'll also go into avoided costs in more detail, and set up the supplemental technical working group to go through our renewable gas evaluation methodology, the incremental cost methodology, in detail for those who might be new to it and have an interest in any of the tweaks that we've made since the last IRP. So with that, we will take questions, and thank you so much for the great questions throughout the day. And we know it's a long day, and we really do appreciate your time. So thank you. And I don't know, I'll just make sure I'll check with Matt and Tammy and Melissa, see if there's anything else that I'm forgetting before we bid adieu.
Nothing that I can think of, Ryan. Yeah, just echo Ryan's sentiment of thanks for the engagement and sticking around for all afternoon.
Likewise from me as well.
Okay, well, thank you to all the presenters again. Please feel free to reach out to us between these meetings. We love questions, and we learn from your questions and your comments. So thank you, and we hope to see you, and we hope to hear from you in the meantime. But hope to see you at the next technical working group too. Thanks everybody. Have a good week.